Okay, so it's kind of like associativity and distributivity, right? So let's say we have 3 times 2, right? Plus 4 times 2, right? And we want to multiply this guy by say 3, right? I want to multiply this guy by 2. Okay, so it will be, this bracket here adds a layer of complexity, right? The way you're saying now is doing like 3 times 2 plus, let's say 4 times 2. Okay, let me just remove this one. Let's multiply everything by 3, right? So 3 times 2 is 6, right? 4 times 2 is 8. 8 plus 6, that's 14, right? And then this times 3 here. That's what 42, right? But it's actually different from this is okay. This is 3 times 2. I think the for this right there. Okay, so this 3 times 2 is 6, right? Plus 8. Okay, like this one is basically the same thing, right? Okay, the both of them are the same thing. But in a situation where we have like let's check, okay, let's say here is 3 and here is 4, right? So once we've gotten these two values, if we want to reduce first, you're basically saying we should get 14 first, right? And then we multiply 14 by 3. You get, but that may not be the case because of this 4 here. You get, I think like this example I'm using is not portraying the information well. Okay, so let's see something. What is a polynomial like? We have add I, right, times let's say WBC, right, plus more I times WBC, right? So we're doing a multiplication here, and then we're adding the both of them together. Let's say if this add I was 3 and WBC was 4, right? Okay, let's say add I, WBC, then more I is 2. So we have 3 times 4, right? Plus 2 times 4, right? But then like these guys are polynomials, which means they are going to have their own, let's say, they are going to have their evaluations. I think reducing it like this, let's just use an array. let's just use maybe if add I was 0 0 0 0 3 3, right? WBC was 2 3 4 5 plus, let's say Molai was 0 0 2 2, right? Times, let's say 1 2 3 4. I meant to do element-wise multiplication here, right? So multiply the both of them to get one new array, right? And this other one, we multiply it to get one new array, and then we add the both of them to get the final array, right? So, okay, I think this was even the best example to have used. If we reduce first before evaluating, when we do this multiplication, we are going to get a polynomial of a higher degree, right? Because this guy is BC, right? This is BC. When we multiply them, we are going to get B squared C squared. If we do this element-wise multiplication, like this and this, if we multiply them element-wise, we are going to have a polynomial B squared C squared. Is it making sense? And this other one too, we are going to have this BC. We are going to have a polynomial B squared C squared, which you can then add together, right? But in order to represent a polynomial like this, it will need to take us to a higher HC, right? A higher interpolating set, which will be 0 1 2, right? So, but we are still dealing with 4 values, which is 0 0 0 1 1 0 1 1. But in order to represent this polynomial, we are going to need like 0 0 0 1 0 2 1 0 1 1 1 2 2 0 2 1 2 2. You get? So we are going to need more information to actually represent this polynomial, and that is what we are trying to avoid, right? That is why we now do it independently. That's why we partially evaluate them independently before reducing. But if we reduce first, we are just going to get an array of 4 elements, which does not reflect this polynomial. The array of 4 elements will represent, or the polynomial that array of 4 elements will show is basically BC, not B squared C squared. I don't know if it makes sense. So that's why we need to actually do the partial evaluation before we reduce. But it doesn't change the complexity of the program when you're writing the code, right? When you're writing the code, just you already have partial evaluate on each of the ADI, MOLI. You already have partial evaluate on them, so you call the partial evaluate on each of them, on both ADI, WBC, MOLI, WBC. So you call partial evaluate on each of them, and then you reduce. So the reducing is still going to be the same logic, right? You multiply these two, and then you add these two. So it's to avoid this blow up here. That's why we actually partially evaluate each of them before reducing. Does that make sense? Okay. Levy. Have fun. Where are you like implementation wise? Product police, some police. Any challenge? No, so far. Okay. Well, when should we be expecting? Weekend by Monday. So GKR eventually took 1 month. Okay. Goodness. How far? Think you are done now, abi? Eh? Maybe. But have you written the test? It's failing. Okay. Uh, but it's just to debug, right? Like the prover is done, right? The test is the problem. Okay. So it's just to debug. Okay. How far? Okay. Modifying your assumption. The other model you have it implemented now. So it's product poly sample. Okay. But any challenge?
After I watched
Okay. Smart dev. Partial evaluate. Is it for the sum poly or sum poly? Partial evaluate. Okay. Okay, partial proof for sum check. But your sum poly. Okay, you have your sum poly. Okay. Fine. You've not started GKR. Even circuits. Where are you at the moment? Sum check. Hi. But is there any challenge? But like you're way behind, But you need to try to put in efforts to make up. Okay. So today we're supposed to do another code review, right? The essence of this code reviews is for everybody to understand what is going on, right? So it doesn't make sense that somebody's reviewing a person's code and you don't understand what you're supposed to do, and instead of you to like pay attention and ask questions, you don't. So that defeats the essence of the code review. So Cast will be coming to do like a code review. right? And while he's doing it, both those that have implemented and those that have not implemented, everybody should pay attention, right? Ask questions where it's not clear, and um, hopefully all the questions or the things that have been keeping you guys from maybe any challenge you've been having, we'll be able to figure it out. Okay? Okay, sir.
Okay, presenting your record here. I might not use this. I might not use it. Let's just.
You want to know? So you will join us?
I don't know. I might, but I will use yours if need be.
So let me be here helping with the switches. Right.
Is it working?
The meeting.
Can you join the meeting?
PWCV. I think it's should mute.
Okay.
Yeah. Okay. So yeah, you can present. Well, wait. I'm trying to. We need one. We need one person presenting.
We need one.
One person presenting.
One person presenting.
Yeah.
So that's okay. So you have to start presenting.
So maybe when you want to. Maybe when you want to.
Good morning, sir. Good morning, everyone. Alright, so I want to present my code. So just explaining what I did and how I went about doing my own implementation. So Is this clear enough? It's like this thing is slow. Alright. Is it okay like this? Okay. Alright. Is it clear? It's full screen here.
Where's the green? There, probably maybe too. The green and the left.
The mouse button top left.
Like this.
No,
Like
no,
the
no,
button.
no.
Okay. Oh, this guy.
Yeah.
This is from the meeting.
I think it's from the victim.
Yeah.
It's from the victim and Francis laptop. Can you can't say anything. You didn't hear.
I can see you.
Can't you say anything?
Yeah, I'm seeing you.
problem.
Press F11 in that video.
I'm seeing you.
Alt F. Off what? Where's F11?
Because of the red.
Are you sure?
I am coming now.
Don't have screen.
No.
I think I read this fine.
Okay. What can I do? Leave it.
Is this color okay? Is you I'm asking you, please. Is this color okay? I'm trying to look for. Should I use?
Sometimes go.
This color self, me I no go feel understand what
What?
Make you like that.
Apart from it, there is anybody that cannot see the screen.
Off light, they will see them. No.
Okay, off lights now.
Which like have you have given
Off light. Off light.
What are you
Off light, you will see.
Yeah.
But I think if it's Zoom,
But it's actually it's only because having issues with the color.
like especially from far.
How you see?
From far, the color is. I can see it.
Oh, okay. The moment is that it looks like arrow.
Oh,
Like it looks like lots of.
errors. Errors.
Like the color.
Okay, let me just use this. The funny thing is, if I use another thing, it might be hard for me to retrieve. Like my head is used to
You can work with it, but
Okay,
just
okay. All right. So I'm sorry about
maybe
this.
just zoom in a bit.
I'm sorry about the colors. Maybe I'll try to work with another team later, but for now, if I use another team, I might not understand this. All right. So should I start from the imports? Do we need to start from the imports? All right. So basically, this is my proof structure. So I have the claimed output, which is like the claimed sum, and I have my sum check proofs. Yeah, so my sum check proof is like a vector of GKR sum check proof, prover proof. So I have a struct in my GKR sum check, so that it's called GKR sum check prover proof, because I also have a verifier struct as well, so I just named it like that. Then this WB evals is a vector that holds the evaluations of WB polynomials, and the WC evals is a vector that holds the evaluations of the WC polynomial, because we know that the verifier is not supposed to know the WB polynomials. So if the prover is performing its computation, it needs to be able to send the evaluation of the WB polynomials and the WC polynomial to the verifier, so that they can use it for their own verification and all. That's why I'm holding it here. So please, if in case you're confused at any point, just let me know. I might skip something, so if you call my attention to it, then I'll possibly do justice to it. All right. So this is my proof function. So it's taking in the circuit and it's taking in the input. So one of the reasons why I'm taking in the circuit is because I have to evaluate here. Because the proof is it's basically running. You're trying to prove that a circuit. So you're basically trying to prove that the evaluation of a certain input over a circuit actually gave a particular output. So that means we really need to like evaluate the circuit. So that's the first thing I'm doing here, to like evaluate the circuit.
Sorry, Pat.
Yeah.
I thought Wisdom said there was no need for that, because basically GKR is just to test if the result, is to test the result of the circuit as against the circuit.
To test the result.
Like maybe you have evaluated the circuit now and get the result. So GKR protocol is just to test if that result came from that circuit. Just like subject now, we don't really, like when you evaluate the polynomial, you're not supposed to evaluate it inside something. You evaluate it outside and not passing the sum and then evaluating the subject. So but then, is it necessary to like passing this subject and evaluation, but evaluate inside the group?
Okay, so while I was implementing this, I've tried a lot of things. So I decided to evaluate mine inside the circuit. But you can actually like evaluate it outside then and pass it. But this is how I went about implementing mine. And that thing is, there's a place in my verifier where I needed to make use of the so that Wisdom said that the prover and the verifier knows the circuit, right? So, and if the prover and the verifier knows the circuit, the verifier is meant to evaluate the circuit, right? Sorry, the prover is meant to evaluate the circuit. So when the prover evaluates the circuit, he's now trying to like prove that the output of that circuit was like correctly computed and all. So this is me like evaluating the prover evaluating the circuit at this line, and with this the prover now have access to the circuit that he evaluated, so that he can perform the rest of the checks. All right. Any other question? Okay. So on line 26, instantiating a new transcript. Line 27 is a vector where I'm basically like pushing all my layer proofs. So for every layer you get your proofs. So I will be pushing them into this layer proofs and all. So line line 28 is my WB eval. So this is going to be a vector that will hold the evaluation of the W polynomials at every layer. So for the WB to hold for WB, and the WC is going to hold for WC. So, and you know that the WB and the WC polynomials are actually the same, but we are just holding them separately so that we can blow them up using tensor-wise addition and multiplication and all. Then here I'm holding my alpha and beta on line 30 and 31. So on line 30, I'm setting it to 0, and line 31 I'm setting my beta to 0. So in my loop at layer in the when you're looping in the first iteration where it's like index 0, this guy is going to be like 0, and you're not using it in your computation. So in the process of that iteration, it's going to update the alpha beta. So when it comes in the second iteration, which will be at index 1, alpha beta must have been updated, and that is where we are going to use alpha beta to compute our FBC polynomial. So that's why I'm setting it at 0 here. Then the ROB values and the ROC values. So these are just, it's a vector that holds the random challenges which we'll be using. So we are going to see how we use it in the computation, which we'll be using to like partial evaluate our polynomial as we proceed. All right. So you know, in the way you work with your circuit, the first thing you need to do first is you get the W0 polynomial, which is the output polynomial. Are you guys following? So you get the W0 polynomial, which is the output polynomial. So what I'm doing here, I'm checking if the length of the output polynomial is 1. If it's 1, I'm appending an extra 0 so that you can have 2 values, which you can actually use as a polynomial to carry out an evaluation and all. So if you look here, the way my W polynomial is, it has my multilinear polynomial, it has a member in a struct that is called evaluated values, and that evaluated values is a vector of field elements. So I'm checking if the length of the evaluated values is equal to 1. If it's equal to 1, I'm padding a 0, so I'm pushing 0 into, I created a new variable which is mutable, so I'm setting it to the evaluated value. So I'm pushing 0 into it, then I'm using it to create a new polynomial, passing in this value. So this is going to update this W polynomial to whatever it's coming from this guy. So we have a polynomial now with an extra 0. So for instance, if maybe our output was 80, and with this stuff it's going to be 80, 0. So this will now be our W0 polynomial. All right. Please, are you guys following?
So this particular thing that you did, this is supposed to be done like adding appending 1 0 to the output.
Yes.
It's supposed to be done inside the GKR.
Yeah, it's supposed to be done here. So the way Oba went about doing his own, he created a separate function for it. So, but me, I'm doing mine inside here. So that's that. If you saw its explanation, yesterday, it has a function that calls either initiate protocol or start protocol. So he was doing that inside that initiate protocol function. Because if you followed what Wisdom explained in class, when you're done evaluating your circuit and you have your output, right? Before, the first thing you need to do, like when you have that your output polynomial, you have to first append it to your transcript. When you append it to your transcript, you generate randomness, and you now use the randomness to evaluate that polynomial. When you evaluate that polynomial, it's going to give you a claim sum. But now, if it's just one value, you cannot take one output, like one value as a polynomial. You understand? So for you to actually work with it, you have to like append something to it to make it an actual polynomial. You cannot work with just one value as a polynomial. So you append 0 to it, to make it a polynomial. You know how our multilinear polynomial structure is. I don't know if that makes sense. Okay, so now after doing this, what this is basically doing is just appending 0 to this polynomial if the output is just 1. So once it appends this 0 to it, we now have an actual polynomial. So what we are going to do now, we are going to now append that polynomial into our transcript. So I have a method in my multilinear polynomial called convert to bytes, and you know our transcript doesn't just take polynomial, you have to convert it to bytes first before you can append it to the transcript. So that's what I'm doing here. I'm taking the W polynomial, converting it to bytes, and I'm appending it. So once I do that, I call the random challenge as field element. So this would give me a random challenge arrow A. That's why I call it random challenge A, because that is like the first random challenge. So once I get that random challenge, I'll now evaluate this our W polynomial at that random challenge, and the evaluate function is taking in an array. It's taking in an array. So I'll pass the random challenge to a vector, which is just going to be a vector of one value, and it's going to get our claim sum. So this is going to be our initial claim sum. Any question before I proceed? Question?
So I wanted to ask about the length of arrows, which we've done that.
Okay, no, I've not done it. Yeah, I've not done it.
Since you're passing an array from since that's the needs to actually count the numbers.
The reason why you're counting number of arrows in this case is imagine it's more than one or two. Let's say it's 3, 4, 5, this thing. So you know that what you're evaluating as now is not just one bit.
I think that this is not where that scenario is important. This is where that scenario is important.
It's when you are getting your.
It's where you're partial evaluating. This is where that scenario is important.
It's also important when you are doing like your own zero. Do you get what I'm saying?
Yes.
So I also have like one other. We'll continue.
No, I point it out.
So I wanted to like ask for scenarios where like I feel like what we are basically working with now is imagining that almost every layer, basically, maybe apart from the output, would always be like raised to the power of 2, so that the 2 raised to the power n polynomial, right? Okay, so imagine the inputs most of us work with like will be 8 inputs.
Yeah.
Right. But imagine your inputs are like 6, for example. Right. You know, from that 6 now we are going to 3.
Yeah.
Right. They are going to like whatever happens, right? So in that case, like from the input you don't even have a polynomial that is like 2 raised to the power n, because 6 is I don't know if you get what I'm saying.
Yeah.
So in that case, like, do we just basically start padding from there to like make, you know, we can initialize our material polynomial with just 6. So in that case, we just basically start padding with zeros or so. Then we know that, oh, if we want to get maybe the number of outputs at a specific bit, we are basically looking at the number of bits in that layer and can just take the first n. Do you get what I'm saying?
Yeah, but I think normally if I think I don't know if it was Wisdom that mentioned this or Francis, that if the polynomial is like 6, like the input is like 6, that you need to like just pad it to make it 8 with zeros to make it 8. If you pad it with extra zeros to make it 8, the way it's going to build up, it's going to build up to give you an output that will just work with those zeros. So in that case, I don't think there's a problem, because once you pad it with those zeros, it just goes with 0, 0, 0 upwards.
That's what I'm just like trying to mention.
What bit do you pilot?
No, I'm not even padding. I'm not even padding basically. That's what I'm saying. Like from that, like once you are getting the layered evaluations, like,
Yeah.
you just have to check if that particular layer right from the input basically.
Yeah.
You don't even need a layer to evaluate, like the gate layer to evaluate anything. You just check that W poly. Once you are trying to create that like multilinear polynomial, basically, you just always have to check that is this length up to like the power of 2.
Okay.
If not, you just have to find the next power of 2 and pad with zeros. So you don't need to like evaluate anything with the gates.
If you start with 6, the next one is 4.
Yes. So you pad to 4.
But
The next one
so,
is 3.
so if instead of doing that computation, that's checking every layer to pad it with, if you pad the input, you wouldn't have to do that anymore.
Or will get to complete.
If you are, no, what you are trying to say then will be that you just have to start adding like extra bits. If you are saying that right from the input is pad, you don't have to like do any other thing, right? What you are trying to say is that you just have to start adding like extra bits.
They don't necessarily
Even if you add extra gates, it doesn't hold anything because 2 zeros will always go to 0, whether you're adding or you're multiplying.
Now let's do it like this.
But there are 3, you're just adding one more.
So we have 6, we add 2 zeros to make it 8.
Yeah,
Now,
but this 2, but this one now is 0.
I don't know.
That's what I'm saying. So, you know, basically, we start initializing our circuits even before knowing what inputs to evaluate at. You agree with me? So now, let's see from the first layer, you have just 3 gates in your circuits. From that first layer, you know right now, in the one we use 8, we have 4. So imagine you have just 3 gates in that first layer, right? That means 6 inputs are going in there.
You need this.
I'm very serious. The game. So my errors.
It's not sharing.
No, okay, don't worry. Like, if they call, they will just join.
Huh?
Like, don't worry. If they
So,
call,
so that they'll be seeing this stuff now. They are not saying. Okay, switch.
yeah.
You are trying to save for the thing from this is where it's the next. You can have one of these going into 2 days.
Yeah, but they were going through the country.
Find it too, yes. They find it too necessarily does not mean that 2 different inputs are going to mine is different. Because you share your gauge basically has
I share.
Sharing, but since network.
Yeah,
Let me-
I'm telling you.
It's my fault. Since it's network, I'm just leave and join back.
Okay, sharing. Alright.
Can I write the circuits? Write the circuits.
Alright. So
So 1, 2, 3, 4, 5, 6.
1, 2, 3, 4, 5, 6.
So all going into like 3 gates. Yes. So you can write any addition or any.
Okay.
Right. So that's 3, 3, 7. Yes. So that second one and the third one goes into another gate. Yes. That
Okay.
one, the second one and the third one go into another gate.
This one.
Yes.
But then does that not defeat having only one output from the gate?
It doesn't define
These two will go as
Yeah, add plus and
5 and 6.
yeah. So that's 11 now. We
Mhm.
can add another gate again.
Okay, this will give us 10 here, and this will give us 18 here.
You forgot to write the
We
gate.
get
Okay,
Then maybe final one is add 2.
mm-hmm.
And
So
you
give
get-
us 28.
right. So in this case now, right,
Mm-hmm.
if you are padding, if what you are saying is if we start padding from the inputs, that we don't have to worry about any other polynomial.
Mm-hmm.
What, if you are going that route, it means that you have to add like an extra gate. And what I'm trying to say is, because our circuit is initialized before even knowing what number of inputs to pass in, our circuit will just have 3, 2, 1, like 3 gates for layer 1,
Mm-hmm.
2 gates for layer 2, and 1 gate outside. So I'm saying we don't care about the number of gates in each layer. All we need to know is for every layer of W's that we go to, we just have to check, is that layer a power of 2? If it is not, pad is 0, that's all.
Okay, I get what you're saying now.
Yeah.
Can I say something?
Yeah.
So, even if we decide to pad this input with 2, like 0
Zero,
for
yeah.
7 and 0 for 8, that does not mean, sorry, that does not mean we need to add a new gate. You get? So we can just pad it. Why are we padding this guy? We're padding him because of the WNLA. Because when we want to create that W polynomial, it has to be the power of 2. Right? So even if we pad this guy, that does not mean we need to change the circuit. Because each of these gates know exactly what they want.
Yes.
Right? And they are going to pick it from the inputs. Even if this input was up to 1 million values, right?
It's not.
The
We
gates
already
know
where
what
to
they want.
pick us from.
Yes. So we can pad this guy to make him a power of 2. We can pad all of them. Just so that when we want to create out of blue polynomial, so it will be straightforward. Or if you want to ask, if you want to handle that here, you can. If you want to handle that in your multilinear polynomial, you can. Right. But I think it will be best handled on the input, not in the multilinear. Because if you move that to the multilinear, but you know, like the multilinear polynomial library you guys wrote, it does not care about circuits. It does not care about, like, the library. Anybody should be able to create a multilinear polynomial and do whatever the person wants with it, right? So that should not, what we are doing here should not force that to change.
So,
This is GKR.
but for our current implementation, is that gate not wrong?
It's
You know,
valid.
It's not.
Our current implementation states that you have an input, you have an output, you have an operation, you have a left, right operation and an output. But this one now has left, right operation and 2 outputs.
It's
But what I'm
not
saying
wrong.
so is, if this is not 2 outputs, this the one that's on 3 and 4.
So my implementation handles this actually.
How many of these implementation?
Because my implementation I'm basically using like left index, right index, and output index. So I specify the output where I want it to go to. You understand? So
So
And-
we are looking at it from like output
It's the
of.
gates that determine what they want.
So in this case now, the gate that has 7, basically. Sorry. So from 7, like the gate that has 7, basically says the output is at index 1, right? Then the left is at index 2, that which has that 3 there, and the right is at index 3, which has 4.
Okay, I'm looking at it from
I don't know, sorry, just
I guess
So,
So, in this layer,
Let's
in this
Pass.
layer,
Sorry, Frank is saying you should go ahead. So go ahead. Like explain what that gate.
okay, so what is happening here now? You know, normally in your gate, you have your left index, your right index, and your output index, right? Now, in this gate, what you're basically doing, you're saying the first gate, the left index will be 0, the right index will be 1. The second gate, the left index will be 1, and the right index will be 2. You understand? But normally, the picture of what we have been doing is the left index is 0, right index is 1, left index is 2, right index is 3. You understand? So you can, in your gate, you can tell it what to do from here. So in your gate, you can say left index 0, right index 1. The next one, the left index will be 1, the right index will be 2. So with that, you build this guy.
So let me just say something. Like when we started looking at GKR, we said something about fanning too, right? Fanning too. So that's a fan in two. But we didn't say anything about fan out, right? So this two is basically fan in, what is coming in, right? And it's giving out just one output. But this other guys, it's them that is now deciding what they want their input to be. You get it? So fan out is technically, you can think of it, it's technically one, but it doesn't care how many other people come to take that. I'm giving out one thing. I don't care about how many people decide to take what I'm giving out.
So if you want to write the Boolean hypercube representation of this gate 10 and gate 18, that would be 0, 0, just right, for 10 and 18.
No problem. It should be 0, 0, right? 0, 1.
You see that's
That would be one.
that's what I was looking at.
But
So which one will be 1, 0, which one will be 1, 1?
1 will be 0.
1, 1 will be 0.
Yeah, there's nothing there.
So that's where you do the padding, right?
Yeah.
Without 0. So
That was
just
0.
one random 0.
So if we do this padding in our circuit, right?
Is this?
That's the 1 0 now.
Yeah, it's
So
0.
that third
Sorry,
that
I beg,
third one
wait.
is 1, 0.
You press, just press
But the last one will be. It's just like the way we've had all the multiple.
Should we actually do this padding in the circuit or do it in our GKR?
Then the one you said that you
Because I
said,
feel it's because of GKR. That's why we need to do the padding.
the padding. Well, are we doing it in the, like, the circuit does not care. Right? The circuit does not change.
Monotonial, we even reject it if it's not a multiple, if it's not in a power of 2.
Exactly.
What changes is the result, the W polynomial. We can just pad it.
what
Right?
if we have 7?
7 inputs.
Yeah. Bad last.
Yeah, we pad it to negative power.
What gate will you give those last?
We don't need to get it.
You can do it the same way we did it for this one that has 7. Maybe it's the 6th and
You can add
maybe it's the 6th and the 7th
eight.
one that will now enter into
Yeah.
This is
another.
inputs, so I can say, okay, let's do this.
No.
So
don't need
these
to
are
do
the
it.
inputs, but
Yeah.
nobody cares about them.
You only padded 8. You care about 7, right?
No.
This
Say
guy,
what if we have
this
7?
guy
So
will
we have
basically
7.
be.
You care about 7.
So write the 7 cars.
It's only 8 to padded.
So what we have 7.
7 inputs, write the
Okay.
7.
This 7.
Then let 6 and 7 maybe go into another gate.
Okay.
Okay, you take one from.
Yeah.
So whatever you're padding, no point.
Come on, this gate there.
But you still need to pad in order to get your W polynomial.
Okay, eventually from that.
Exactly.
Abby?
Yes.
even this guy can come from
to one, exactly.
Yeah.
Yes.
Can what?
Can be anywhere. Like this guy can be 7 and 1.
Yeah.
Exactly.
You get
It's the gate that decide what's inclusive.
I think that
The gates decide.
And has to side by side.
So, like, I'm happy that we are understanding it, because initially, if we started explaining it this way, trust me, a lot of you will be lost. Maybe we started drawing those random lines.
Some people not mistake the 11 as after the 10.
The 11.
As the value after 10.
Oh, okay.
Like they'll not mistake the 11 as
I should remove this guy.
as a
now.
label, so they don't mistake.
Alright.
Okay. So we can continue.
Yeah.
Oh, people of God.
Okay.
So,
No need.
yes,
No need, you can share.
I can say Abu.
They've already started timing us. So we'll just be switching.
Alright. Alright. When did I stop?
You're at W0.
Here? Or here?
No, before applying to transcript.
Alright.
The claim source.
Alright, so let me just go right again. So now, like I said, when we evaluate our circuit and we have like one output, in order to actually work with that, each of the layer evaluations is what we consider as our W polynomials, right? And for us to actually work with the layer output, it has to be in form of a multilinear polynomial, and having just one value doesn't give you a multilinear polynomial representation. That's in evaluation form. So we have to pad it with 1, 0. So we check if the length is 1. If it's 1, we pad it with 1, 0, so that it will give us like a multilinear polynomial representation in evaluation form. So once we do that, you know that now this guy will be updated. See where we are updating it here. So this guy will now be a polynomial that is padded with a 0 and all. So what we do next is we append that polynomial into our transcript. Sorry. So we append that polynomial into our transcript, but remember that we always convert to byte first before we append. And once we do that, we sample our random challenge, which is RA. And when we sample that random challenge, we use it to evaluate that polynomial at that random challenge. And once we do that, we get our claim sum, and that claim sum is what is our M0. Are we good?
Yeah.
Alright. Now, once we get our M0, which is the first claim sum, now we are starting our loop. So inside this loop, we are looping based on the number of layers. Now, remember what we are trying to do is we are trying to prove that, let me just do this guy. You know that the W0 is equal to the FBC polynomial using the W polys of the layer below it, right? So we are trying to prove that this claim sum is equal to the FBC polynomial when you use the W values of the layer below it. That's what we are trying to prove here right now. You didn't get? So I don't know if Francis can come and open this. Francis, please, can you open this stuff? Yeah, I'm not used to stuff, so. Alright. So, how do I I make it?
I need to do that. Seems it's not sharing.
Are you with us now? All right. So let's say we have 1, 2, 3, 4, 5, 6. I'm wait to move this thing. 7, 8. So this goes into this guy. 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 So we have this guy here. So this comes here. So I'm just going to use plus plus. Okay. Plus plus. Oh, sorry, it's supposed to be here. So this is going to give us 3. This is going to give us 7. This is going to give us 11, and this is going to give us 15, right? Yeah, 15. So it's okay. So this is going to give us 10. This will give us 26, right? 26, and we have another plus gate here. So this is going to give us 30, right? Now, sorry, 36. All right. Now, this guy here is our W0 polynomial, which is our output, right? And because this guy is just one value, we cannot use it like this. So we have to add 0 to it. So we now have 36, 0, right? Now, once we have this 36, 0, we append this to transcript, right? And once we append this to a transcript, we'll get a random challenge, which is arrow A, right? Now, when we evaluate this guy at arrow A, we are going to get a claimed sum, which is our M0. Are we good? Now, you know that this is W0, right? And W0 is equal to summation of add I, sorry, equals to summation of add I plus 1, which is 0 plus 1. No, sorry, not add I plus 1, is this thing, which is add 0, right? Add 0 of A, B, C, right? Times W 0 plus 1 of B plus W 0 plus 1 of C, right? Everything will be added to mod 0 of A, B, C times W 0 plus 1 of B times W 0 plus 1 of C, right? Now, this is what we are trying to prove. This is the claim sum, which is M0. Now, inside this loop, we are trying to compute the FBC polynomial for the layer below, because we want to prove that the FBC polynomial of this, the FBC polynomial of W0 will make use of the W of the layer below. That's why we are having 0 plus 1 here. So that's what we are trying to do now. Does that make sense now? All right. Sorry. No, to resume. Alright. Okay. So, where's my loop? Alright. So now we are doing for layer index in 0 into the circuit.layers.length. You know our layer is from ground up, so it has a length. So we are looping from the layer 0, that's from the top this thing. So the way I implemented my layer is I implemented it in reversed form. So the one at the top will be at the first of my array. So yeah, so the input will be at the last and the output will be at the first index. So if we are looping through this, so it's going to start with the first one, which is the output guide. All right. So okay, the way this thing is big is choking my eyes. All right. So now we are trying to get our ABC, ADI ABC and our MOLI ABC, which we can get from the circuit because we implemented it in our circuit. Are you following?
Yes.
Which you can get from the circuit and all. Now, and you know that from our equation, what we are trying to multiply the ADI with has just BC in there. You understand? So, for instance, you know, the ADI ABC is going to multiply with the WB plus WC, and the MOLI ABC is going to multiply with the WB times WC. Now, if you blow up WB plus WC, it's going to give you WBC, and if you blow up WB times WC, it's going to also give you WBC. Now you see that we have BC in both of them, but in the ADI and the MOLI we still have ABC. So in order to remove the A, we have to partial evaluate A so that we have BC in the ADI and BC in the MOLI, so that you can work with both of them so that they'll have the same variables. Does that make sense? Are we thinking? All right. So that is why we are doing this. So we are getting our ADI ABC polynomial, and we are partial evaluating it with that first random challenge to remove A. We are doing the same thing with our MOLI ABC, and we are partial evaluating it at that random challenge to remove A. So now we are going to have ADI BC. That's why ADI BC here. So the A is no longer there. Are you following? The A is no longer there. With this ADI BC and this MOLI BC now, you can comfortably work with the WBC. Is it sinking? All right. So what I did here, I have two ways of getting my ADI BC and my MOLI BC. So for the layer 0, I just do, so that is the correction I'm going to go back to, because now I'm doing this because I'm assuming that the output layer will always be 1, and we are just going to pad with 1 0. But in a scenario where the output poly is not just one value, let's say we have 4 values, you know our random challenges will not be 1. So I need to solve that in my code and all. So but the way I'm handling that now is, for layer 0, I'm just partial evaluating the ADI ABC at the arrow A. But now for other layers, I have a function called compute ADI MOLI, which is going to make use of the alpha beta to perform that linear combination and all. So let's just go to that function so we are able to see what is happening now. But you know that this function will not run at the first iteration. You understand? It won't run at the first iteration, because at the first iteration this will be 0, and we are checking if layer index is equal to 0, use this guy, but if it's not equal to 0, hit this guy. So at the first iteration is not going to run, and another reason why it shouldn't run is because at this point the alpha beta is 0, right? All right. Now let's look at the compute ADI MOLI. Let me just go to it here. All right, so this guy is a bit It's a bit complex, though. Small complex. So the compute ADI molar is taking the alpha, beta, and it's taking the ADI ABC for that layer and the molar ABC for that layer. Then it's taking the ROB, that's the randomness, the ROB values and the ROC values, which is going to use to partial evaluate. I think I need to open that I think I have it here. Let me open it so that you understand what is going on here. Yes. So now, so you see that our new ADI is using alpha and is multiplying it with ADI when it has been partially evaluated at ROB, and is adding it with beta times ADI when it has been partially evaluated at ROC. So if you look at what is happening here, I'm taking in my alpha and my beta. This is my ABC. This is my ROB values. This is my ROC values, which is representing ROC and ROB. Are you getting? Now, what I'm doing here now is I'm now doing add ROB BC. So this is for this guy, add ROB BC. Are you seeing it? So this add ROB BC will now be that the multilinear. I'll call the partial evaluate, and I'll pass in the ADI ABC, and I'll call the evaluated values, because my multilinear has a vector that has evaluated values, which is a vector of field elements. Then I'll now partial evaluate at the first index, which is A, using the ROB values. Now, the reason why I'm doing this, normally I would have looped through this whole stuff to handle this, but I'm trying not to use clone at all in my code, right? So what I did here was I first evaluate at the first random value, then I now loop here, skipping the first one and looping through the remaining ones. What this means is that this, because clone has it has an overhead when it comes to memory usage. Using so many clone in your code is like is affecting your memory. Yeah, creating a lot of thank you. So our ROB might be something like this. Let's say 7,6,0,8, depending on the number of bits in that layer, right? Now, so my partial evaluate in my multilinear is only taking one value, and it's partial evaluating at the first index. So it's not making use of a loop, my partial evaluate. So normally some persons make their partial evaluate to take in an array, loop through the array and partial evaluate their polynomial. But mine is just taking in the value, the variable you want to partial evaluate and the value you want to use in partial evaluating it. Are you getting it? So, but now since we want to partial evaluate at multiple random values, so I have to loop through the array and partial evaluate that guy. So that is what I'm doing here. So normally I would have just done this guy, like loop through the values and partial evaluate everything. But when I first wrote the code, I was making use of clones everywhere. So in order to remove that clone, what I first did, I partial evaluated at the first randomness, right, which is the first guy in this array. Then in the subsequent rounds, it's going to skip this guy and continue with this one. That is why you have this skip one here.
But it's not full evaluation.
This is not full evaluation. It's partial. You know, you are partial evaluating based on the bits.
But you have all of the bits value. You have all of the value.
You're still partial evaluating at index A. You know, you're still partial evaluating at that index A, but you're partial evaluating based on the bits, like the number of bits of that layer.
So it can be A1, A2, A3, B1, B2, B3, B4, C1, C2, C3, C4. Right. So for that A now,
you need to get all the A's, like A1, A2, A3. So it's partially evaluate for all the A's. But you still have, like, after partially evaluating all the A's, you still have B's and the C's.
So it's just like if the output index is something like this, if the output index is marked with, is labeled with 00, right, or 01, you know that here now we have two values where you have to partial evaluate. And if the output index is 00, that means the input index will be 000 and 001 or something like that. So now this is considered as a separate value on their own, and these are considered as separate values on their own. So if you're partial evaluating A, based on the number of rounds, you're partial evaluating this one first, you have to partial evaluate this one again, so to remove A. Why these three and these three will be B and C. Does it make sense? Alright. I don't know if anybody has any question, or if this my explanation is not on point, you can call my attention back to it so I can find a better way to explain it. Are you guys following?
Yes, sir.
Peter.
Sir.
Alright. Okay, so
You said because you don't want to use clone,
yeah.
you guys evaluated to 0.
Yeah,
Then
first.
you went to the next one.
Then I skipped. Yes.
To use one.
Yes.
Yeah.
Yeah. So normally, I don't know if I should start rewriting it the way it should have been, but normally what would have happened here is I would do something like this ABC.
Okay, you just comment it out, right? Then do from 0. Yeah.
From
Something like
sorry, I did.
okay, like normally there'll be no need for this,
Yes.
right?
Yeah.
Then you do from 0.
From
yeah.
0,
But then like this one would be the actual poly.
actual poly.
But
But
you need to
you
clone
need to
it.
clone it. Does it make sense? Alright.
Okay, the next is anyone.
Huh?
Just,
Yes.
let's do the switch.
Just send you the
I don't even know what else is. It's definitely normal. Have you left?
Hmm? Okay, let me check.
Leave that one. So. Are you sure?
Yeah, let me resume my share. Alright. So
Sorry. This guy. Don't OBS to deceive us.
okay.
Just need to be sure. Okay. I think I can tell.
Alright. So
Sorry.
alright, so let me reiterate through this guy again. So what I'm basically doing here is, where is that guy? Yeah, so based on this equation we have here, what I'm trying to do here is to compute my new ADI and my new MOLI, because in the new ADI and the new MOLI we are going to make use of the alpha beta this thing, linear linear something. So that's what we are going to use here. So in this guy, I'm taking in my alpha and my beta. I'm taking in the ADI ABC and the MOLI ABC. I'm also taking in the random challenges, that's arrow B values and arrow C values, right? And this is going to be an array based on the number of bits of that layer. Are you getting? Based on the number of bits of that layer, that's what is going to, this thing is going to be. Now, let's say in layer 2, let's say we are in layer 2, A is going to be 0, like it's going to be 2 bits. And A is going to be 2 bits. You understand? In layer 2, A is going to be 2 bits. So, and if A is going to be 2 bits, this arrow B values is going to contain an array of two elements, two field elements, right? Now you want to evaluate A at the first bit and the second bit. So you're going to loop through the arrow B values and you evaluate A at the first and the second bit. So you evaluate A at the first bit with the first arrow B value. You evaluate A at the second bit with the second arrow B value. Is that making sense? Big man, are you following? Thinking about it. So that is what is actually happening here. So normally, the way I implemented it at first, after implementing it, I saw there was so many clones in my code. So I now had to look for a way to not use clones. So what I did first was I set the arrow, I made it a mutable variable, and I set this thing just a pop up and down. So I made it mutable, and I evaluated at the first arrow B value. Then in the loop now, I skipped the first value and I evaluated at the other ones. So at the end of the day, we are going to have our arrow BC, our add BC evaluated at arrow B, and we're also going to have our add BC evaluated at arrow C, which is what we are doing here. This is our add I evaluated at arrow B and our add I evaluated at arrow C. Are you seeing it? All right. So similarly, we are going to do the same thing for mol BC, and you know we are evaluating at arrow B and arrow C as well. So we are going to repeat the same process for both of them. And once we do that, we are going to get the actual add arrow B BC and mol arrow B BC, and we get our add arrow C BC and mol arrow C BC. Then once we do that, this is where we are now doing our normal guy. So our new add I is going to be the add arrow B BC scalar mod alpha, which is this guy. Add arrow BC multiplying alpha. Are you seeing it?
Yeah.
Then, and this plus, sorry. So I have a method called add polynomials. So it's going to do multilinear polynomial, add polynomials, add arrow BC scalar mod alpha, and add arrow C BC scalar mod beta, which is this guy. So this add you're seeing here, this add now is what this add polynomials method is doing. Are you following?
Yes.
Because polynomial, you can't just do plus on two polynomials unless you did an add trait on your polynomial, but I didn't write an add trait or add method for my polynomial. So I have a method like an associated function or associative function called add polynomials that takes in two polynomials and add them together. You can't just do polynomial plus polynomial. You can only do that if you now, there's something Wisdom did one day in class that he overwrote, he implemented the add trait for polynomial. So you basically do the same thing inside that trait. So you can just do this plus this and it will work. That one is better.
It's like you implementing that for that operator,
It's,
for instance, that operator will have an implementation.
so it's basically, what if you want to do that, what you just do is you implement add trait for your polynomial struct. So when you do add trait for your polynomial struct, inside the implementation, what you're now going to do is the actual code that you have in this add polynomial. So now when you do polynomial plus polynomial, it's going to look for that add trait and it perform the addition for you. Don't worry, don't think about it too much. I didn't do it because
I did direct addition and it worked.
direct addition of two polynomials. Maybe you implemented add trait for your this thing now.
No, I
You use add trait from prime field.
You can actually add together. Just elements, depending like element plus addition.
Element, no, like if you do multilinear polynomial plus multilinear polynomial, would that work?
Like, so long your function.
If you didn't implement add trait for your multilinear.
Is that what you're saying?
So he's saying he did multilinear plus multilinear polynomial and it worked. So I'm asking him, did he implement add trait for his multilinear?
I think maybe he implemented add trait.
Maybe you implemented add trait that you don't know. Please, Francis, can you add two polynomials if you don't implement add trait? You can't now.
What did you write?
What have you done? You're basically the one that defines the structure. The program does not know what your structure is.
What you did.
And it does not know how to add it. So you're the only person that can tell the program, this is my structure. And whenever I want to add, this is what I want to add. So don't worry, we know what's happening. No, we know that's
What happened?
you know what happened. You know what happened.
You know what happened.
How? I don't understand.
Go to the app.
No, we know. We understand. Francis, I'm confused. You come and look at
No, calm down.
Like now.
We reviewed these codes, right? We know.
And you saw patterns.
We know.
No.
You get?
This particular one.
Okay, there are others.
When I'm doing
Apart from this one. Louder.
why?
Like the drift, So for the tensor, you can decide to write. You can decide to make it a trait. You get. But that's like totally up to you. Having it as a function still works.
Yeah, that's what I did and it worked. And
No, it will work.
why they call it?
Where you're confusing, this is not tensor.
I know this is not tensor. I'm just asking generally.
Okay.
But you did it.
That when I it will
Yeah.
work without.
No, it's not. This is not tensor.
Implementing trait form.
This is not tensor. This one you're adding two polynomials together, so you're adding them.
Elements.
Yes.
Element twice. Like in order to use that plus sign, if you yes, you have to implement that trait to use the plus sign. Yeah. No, we'll see this.
All right. So the reason why I'm opening this guy so that you guys will like see what we are doing and correlate with it. So remember, this function is just to compute our new addi and our new molli. So if you look at this guy, alpha times this guy plus beta times this guy. So and I have my add polynomial that takes in the add ROB BC scalar mol alpha and the add ROC BC scalar mol beta. So this guy now, this stuff you're seeing here, this one I just highlighted is just this guy like this alpha times this guy. Why this other one here you're seeing like this is beta times this guy. Is it making sense? Now that's the same thing we did for the mol. So the mol, we are still doing add polynomials, taking in the mol ROB BC scalar mol alpha and the mol ROC BC scalar mol beta. So it's just this guy here, alpha multiplying the molli when you're evaluated at ROB and beta multiplying the molli when you're evaluated at ROC. That's what we are doing here. Then I'm returning the new addi and the new molli. This is just raw syntax. Yeah, but it's the same thing actually. That's what's happening here. Does it make sense? Should we proceed? So now we are going back to where we came from. So remember, this was where we came from. So this computation, this function will only run when it is not layer 0. Does it make sense? All right. So now we have our WB polynomial. So the WB polynomial, remember the WB polynomial for every layer is from below. Do you understand? Whenever you hear WB polynomial, the WB polynomial for FBC computation is the layer from below, not the current layer. So that's why we are getting our WB, which is circuit WI polynomial with passing in your layer index plus 1. So it will get from the layer below. For instance, if we're in layer 0, it will get the WB from layer 1. If we're in layer 1, it will get from layer 2. Are we syncing? Similarly, we are getting the WC. So before, what I was doing here before is I was calling this guy again. This same thing I did here, I was calling it here again. But I think it's cheaper to use clone here than to call it again, because when you call it again, it's more expensive. You're like repeating this computation again. So that is why I'm doing this. And remember, this W polynomial, what it's doing is instantiating a new multilinear polynomial from that function. So when you call this again, you're still calling the new function and instantiating a new polynomial. So it's cheaper to just use clone here than to call this again. That is why I don't have any choice than to use clone here. I tried to not use clone, but I have to. All right, now we have gotten our WB and our WC. We have gotten our add IBC and our mol IBC. We can compute our FBC. True or false?
True, Dad.
So now let's compute our FBC. Our FBC, I have a function called compute FBC that takes in the add IBC, the mol BC, the W poly, the WB poly, and the WC poly. So with this, we can compute our guy. So let's go to that guy. Sorry.
This is computer basic for the first.
Huh?
Okay,
Yes. Now it's still.
no, now you're just passing.
Yeah, here we are just trying to get our ADI ABC, our ADI BC and our MOLI BC. And you know, this is different for each layer. For layer 0, it's just this guy, but for layer 1 downwards, you're going to use the alpha beta. So that's why I'm using compute new ADI MOLI here, because I'm passing in alpha beta here. So that's what's happening there. So now that we have gotten our WB polynomial and our WC polynomial, we have to get our FBC, because if you actually want to run some check runs on the FBC. So we have to compute our FBC. So the FBC is taking the ADI BC, the MOLI. So now we have gotten our polynomial of the same variable. This ADI doesn't have A again, and the MOLI doesn't have A again. So it's now BC. Make sense? Alright, so we are passing our ADI BC and our MOLI BC. We are passing our W poly and our WB poly and our WC poly. So now let's hit this function to see what's happening there. So inside this function, this is our compute FBC, right? And this compute FBC uses the ADI. So first thing we are going to do, you know, that's sorry, let me check this guy. Here. So you see that here now, this guy is standing alone, this guy is standing alone, this guy is standing alone, and this guy is standing alone. This is WB and this is WC. This is WB and this is WC. And this is BC. So we need to merge these guys together so that we have WBC, and here too so that we have WBC, so that they can work with this this new ADI BC and this new MOLI BC. Does it make sense? All right. So now when we come here, the first thing we are going to do, we say add WBC. So what we are doing, we say multilinear polynomial tensor add, we take in the WB and the WC. So that tensor add is going to do that blow up that we're supposed to do. So it will cross multiply it to cross add.
Tensor and blow.
Normally we're supposed to blow up before we do element wise addition. But since you mustn't blow up, you can use tensor addition to substitute that blowing up and element wise addition.
No, it was just when you said it, you said it to blow up.
It will still blow it.
You don't need to
Okay, to blow it up, but you don't need to blow
Yeah,
it.
you don't need to blow them separately. To blow them separately.
Particle? Alright. So now this is doing the tensor add to get that your blown polynomial, which will be the ADI WBC. Now for the mol WBC, it's going to do a tensor mol with the WB and the WC to get this guy. And with this guy, we can now compute. So you know our polynomial has this is the add term and this is the mol term, right? This is a side that is handling add because this is ADI, and this is a side that is handling mol. This is the MOLI. So that's why I named it the add term and the mol term. So the add term is basically taking, so I have a product poly that takes in two multilinear polynomials. So this is going to take in a vector of this guy and this guy. So it will create a product poly. And for the mol term, it's going to take in a vector of the MOLI BC and the mol WBC to create a product poly. And our FBC is just going to be a sum poly of two product poly, which will be the add term and the mol term, and we get our FBC polynomial. Any question? Are we good? All right. So let's go back to where we came from.
Can you go to the routine? Can you just walk? Just like where is that? This one. Okay, like is it the blowing of them?
Yes, that is blowing.
The blowing of individual. Can you just go like? Sorry. Sorry.
So it's here now.
Okay.
Okay. So what is basically happening here is let me. Okay. So we have this thing is slow. Okay, yeah. We have the WB pool. It's slow for you. Right? So let me just start up by explaining for you because my mouse is lagging. Yeah. All right. All right. So we have this polynomial WB and we have this polynomial WC, right? And you cannot directly add these two polynomial because they have different variables. This is B and this is C, right? So this is this guy and this is this guy. Now, for you to actually add these two polynomial, what you need to do first of all is to like blow this guy up to have an imaginary C. You understand? Let's say, so this is a evaluation form. It's confusing. I can explain it better in coefficient form. But this is WB and WC. Let's say we have this to be 2A and we have this to be we have this to be 2B and have this to be 3C, right? Now, if you cannot just add 2A and 3C together because they have different variables. So for you to do that, you need to first blow this one up with an imaginary C. You can say plus 0C, right? And you can blow this one with an imaginary B plus 0B. With that, you can now add 0B plus 0B, and you can add 0B plus the B here, and you can now add the 0C with the C here. With that way, you can now have one polynomial that are together. So that is what is happening here. So, but there's another way you can do that, which is what they call that tensor add and tensor more. So, okay. So what they are basically doing here is, now this tensor more. So you see, we have this guy and we have this guy, which is this guy and this guy, right? Now what you're going to do, you're going to say 3 plus 6, right? No, so there are two ways to do it. It's either you blow it up or you use that tensor this thing to handle it. So if you want to blow it up, you have to first blow this guy or blow this guy, then you do element wise. You won't do tensor again. But if you don't want to go through that route of first blowing up and now performing element wise, which is like two steps, you can just use tensor wise straight up, which is one step. So this is a tensor that we are doing here. So you add 3 plus 6, which will give you 9. You add 3 plus 8, which will give you 11, right? You come back to this guy, you do 5 plus 6, which will give you 11, and 5 plus 8, which will give you 13. So it's coming like this guy, this guy, this guy, this guy. That is the tensor add. So similarly, for tensor multiplication, you're still going to do this guy times this guy times this guy. Then you come back here, this guy times this guy times this guy. Does it make sense? So that is what that tensor stuff is doing. So some persons can blow up first and do element twice, which will just, when you blow it up, you add this, and that. Or you can just do this tensor to avoid blowing up and adding. Does it make sense? Okay. All right. So, do you now understand what we did here? Because we have our WB polynomial and our WC polynomial, and we passed it into this tensor add to perform this guy we just did here. Does it make sense? Similarly, we have our WB and WC here to do tensor more. Does it make sense? And this is why we are doing that tensor more and tensor add. You see, WB, WC, we are adding here. WB times WC, we are multiplying here. Does it make sense? All right. So, any question with compute FVC polynomials? All right, let's go back to where we came from. All right. So now we have gotten our FBC polynomial, right? We are now calling sum check, and you know sum check is running on FBC polynomial. So we call sum check, we pass in our FBC polynomial, we pass in our transcript, our claim sum, and we pass in our transcript. Are we good? And this is going to return a proof, a sum check proof. And when we get that proof, we are pushing that proof into our layer, because this proof is for that particular layer. Every layer will have their own proof. So we are pushing this proof into our layer proofs array. So we do layer proofs dot push the sum check proof clone. I wish there was a better way to do this without clone though, but that's that. All right. Now, once we have done this, another work starts here.
Why was he doing this check? Layer index less than.
All right. So the reason why I'm doing this check is because, you know, in my own circuit, it's also taking my layers. It's taking my input as a layer. And I don't want my input to be taken as a layer. You understand? I don't, because if I'm evaluating WB, you know WB is for the layer below. So if I'm evaluating WB, I don't want it to evaluate WB for the input, because the verifier has the input. How are they checking this thing? Alright, is it ready?
Should still be yes, it is.
Alright, so you know that in my own circuit, right, it's seeing the input as a layer, right? And now, you know, when you're evaluating your WB polynomials, which you're going to send to the verifier, you don't need to evaluate the input layer, because the verifier has the input. You get? And the prover can lie on the WB evaluation. So you don't need to send the evaluation as input to the verifier. The verifier has that input, and the verifier can use it for himself, right? So that is why I'm doing this. I'm checking if the layer index is less than circuit.layers minus 1, so that it will not hit the input layer. So it's looping through the whole layers minus 1, which is the last one, that is the input. Does it make sense? Yeah. All right. So now
That means your layer starts from the output.
yes, now that's what I said now, that when I was computing my layer, I did reverse. So that reverse will take the output as the first this thing, and the rest will, like, it will grow like that.
You mean your evaluation or your input? As in when you are setting up your gates, layer by layer. Which one are you using? Are you putting the input at index 0, or you are putting the gates, the layer of your output at your index 0?
So the way I'm structuring my gate, I'm building my gates, I'm building my this thing from ground up. I'm building from ground up. But when I'm evaluating, I'm not evaluating from ground up. I'm evaluating in reverse. Yes, I'm evaluating in reverse. In the sense that as it's evaluating, like, I'm actually, you know, you actually evaluate from ground up, but I'm picking my evaluations in reverse.
Okay, so your output now starts from.
You're not, you know, if you're evaluating, you have to evaluate from ground up to your output.
Yeah.
But you have a vector that holds your layers, right? If I'm picking those layers from that to push it into that vector.
The layer now, which of the layers do you have at index 0?
The layer at index 0 is the output layer.
That's what I'm saying.
But you know, if you're evaluating from ground up, normally your input is supposed to be your index 0. But now if I'm picking those stuff, I'm picking it in reverse. Does that make sense?
It means that array is still how it is. The picking is what you just.
Yes. All right. Should we fire down? Okay. So now I'm getting my random challenges from the sum check challenges. This is our sum check proof, and you know the sum check proof is going to return random challenges, right? Which is the random challenges it used in doing its sum check abracadabra. So I'm getting my random challenges and I'm saving it as sum check challenges. Now, so remember that our first okay, not this guy, okay. So now I'm now evaluating this WB poly and WC poly with the sum check challenges. Remember that it is this evaluation that we are going to give to the verifier, which the verifier is going to use, right? So I want to evaluate these two polynomials so that I can give these evaluations to the verifier. Now what I'm doing, I have a function called evaluate WB WC. So let's go there. So this function is taking in the WB poly and it's also taking the WC poly, and it's taking the sum check challenges, which is the random challenges we got from sum check. So let's hit this guy. So hitting this guy is just a very simple guy. So what it does first is it gets the midpoint of the random challenges. You know the random challenges an array, right? It gets the middle point. So the middle point is basically going to be like, if we have an array of 8 elements, the middle point is going to be 4. You understand? So the first 4 and the last 4, right? So that's what we are doing here. So we get the middle point. Now once we get the middle point, we now say sum check challenges dot split at middle. So it's going to split at the middle, which will give you an array on this side and another array on this side, which is 4, 4. Is that making sense? That is what we are getting here, the arrow B values and the arrow C values. Now, once we get these arrow B values and these arrow C values, we now perform a full evaluation on the WB with the arrow B values and a full evaluation on the WC poly with the arrow C values. This will now give us our evaluated WB and our evaluated WC. That is what this function is returning. So when we go back to where we came from, you see we are getting our evaluation. And now once we get it, we push it inside this WB evals and WC evals, so that this is what the proof, this will be in the proof, so that the verifier can get it as well. Does that make sense? All right. So I need to clean this code. I'm seeing repetitions here. I think it would have been better that I have, so because inside this guy, I'm doing the same thing. Yeah, I can actually move this. Now just create a function that does this evaluation, like does this splitting, because I'm splitting in so many places. So now I want to use the randomness from the blue, split it into two verbs for arrow B and arrow C. So we are doing the same thing. So the sum check challenge is split it into 2. We get our current arrow B values and our current arrow C values, and we set it to this guy because we are going to use this guy again. Okay, now we move to this other part. So here now we are appending. So we are so this thing I implemented this I think 22 hours ago based on what Francis said in class, that whatever we are sending to the verifier, we have to add it to the transcript. That is why I'm adding this guy to the transcript. So first I'm converting it to byte. So I have a function called field element to byte. So I pass in this evaluation and it appends it to the transcript. Then I get the alpha. I do the same thing for the WC evaluation and I get the beta. That was based on yesterday's correction. Then I update my claim sum, and my claim sum will now be that alpha times WB evaluation plus beta times WC evaluation. This is going to be my claim sum based on what we have in the formula. Are we good? Are we good? Any question? Should we proceed
Can you go for this one?
to
After from line 8.
line 80? Okay. So, all right.
Okay, no, one. I think it's.
Okay, you didn't
I
miss
thought
it.
it was on
Okay. Look at it very well.
the appendix.
We good? All right. Any this thing before we move? All right. Let's start with the verify. This is the Ogakwatakata of them. All right. Are we good? So, what the verify is basically doing. The verify is basically doing some of the things that the prover is doing, but it's doing less computation. It's not performing major work because he's receiving a lot of the things he needs from the prover. The part where the verifier will now be convinced is once he gets to the input, because that is what he's sure of, that is what he has. Does it make sense? But every other thing the verifier is getting from the prover, the verifier doesn't trust. So that means in this verifier, the loop that is going, that you're looping is basically comparing what you're receiving from the prover until you get to the last loop where you have the input. So that input now, you're going to use it as your W. That's why the prover is not supposed to send the WB and the WC for the input, because the verifier has it. So the verifier will evaluate the input himself and use it to compare. And that is where the verifier is going to trust whatever the prover sent. So that is like a high level overview of what the verifier is doing. So let's proceed. So everything here, everything from here to here is the same with what we have in the proof, because the verifier is also going to, like, have their transcript, their own transcript, set up their alpha beta. So this previous sum check challenges, we'll be using it like to compute our expected proof or expected claim. So we'll see how we use it. But from here, what you're seeing here is the same thing in the prover. Like, you get your W0 polynomial, which the verifier has. Once you get it, you do the normal appending. So this is a repetition actually. So I'm supposed to just create a function that handles this part, because I'm repeating it, something that is in the prover, and I'm repeating it here. So I'll just refactor this guy later. So this is the same thing. You append the W poly to the transcript. You get your ROA. You evaluate that W poly at the ROA, and you get your initial claim sum. Now we are hitting this loop again, but this loop is going to be a little bit different. Now, what the verifier is checking now is checking if his own claim sum, the one he computed, is equal to the claim sum that the prover sent. You know, the verifier is receiving a proof from the prover, right? He's reading the proof, and he also knows the circuit, right? So yeah, let's proceed. All right. So the verifier is receiving the proof, and from that proof, he has also done his own evaluation to get a claim sum, and he wants to check if the claim sum he got is the same thing the prover sent to him. So if it's not the same, it returns false. So there's no need to even move further, right? So once it does this check and everything works, it moves to the next step. Now, what it's going to do here now is now going to call the verify function from the sum check, passing the proof and passing the proof of the particular layer index. So if the sum check verifier, is taking in the proof. So now, since the verifier wants to verify this particular layer, it's going to pass it the proof of that layer index, and it's passing the transcript. So I'm using the same transcript from the GKR verified across down to the partial verified. So it will pass the transcript too. So now it will now from what it gets here, this verified result, it will now check if is proof it's a struct that has a member called is proof, which is a boolean. So it checks if not is proof, it's going to return false. You know, this is a boolean. So once you negate it, it's going to, like, if it's not, this guy is returning false and all. Okay.
Sorry, this is a verifier. You're calling another verifier instead of a verifier.
Mm-hmm.
Like your normal sum check.
No, I have, look at, let me show you something. So I have proof and verify my sum check. So I have a GKR sum check. I didn't use the normal sum check. I created a different sum check.
But you did show us that part.
Yeah, I did go there. Well, I don't know. Should we go there?
I don't know.
Should we go there?
Yeah.
All right. Let's.
Well, wait first. The people that are going there for, are they following? You're following. You're following. Dean, you're following. Father. Sam, you're done. Okay, but you're following. Jerry, you're following. Oh, you're done.
All right. So let's go to Agile. So I have my sum check. I have my source. I have my GKR sum check. Sum check protocol. Okay. Are we good? We proceed. So, go ahead. I think I should start with the proof. All right. So, first of all, let's look at, I think, instead of calling this GKR prover proof, yeah, okay, prover proof and verifier proof, okay, yeah. So, that still works. So, my proof is taking in some polynomial and claim sum and transcript, right? Now, what it does first is it gets the number of variables, because we are using this number of variables to know, sum check has rounds, and the rounds is based on the number of variables the polynomial has, right? So we are using this number, we are getting this number of variables because that's what we are going to use for our loop, to know the number of times we are going to go through the entire sum check rounds. So the first thing we have here is we have our round univariate polys, which is going to hold our univariate poly, and we have our random challenges vector, and the capacity is going to be the number of variables. So if our number of variables is 3, our random challenges is supposed to be 3 as well. So that's why we are setting this guy here. Then we have our current polynomial. For every time you move, you partial evaluate the first distance and set it to the current poly. So when you come again, the current poly you're going to use will be the updated one. All right. So the first thing we are doing here, we are appending the claim sum here, right? First thing. Then we hit the loop. Now this loop is looping from 0 to the number of variables. So we first get our univariate poly, right?
Yeah.
So this get our univariate poly is where the heavy lifting is actually happening when it comes to this sum check. So let's hit it. So this get univariate poly, first thing it's going to do is going to get the degree. Now we are working with in our product poly. Are you following? In our product poly, we are going to be multiplying 2 polynomials, and when we do that multiplication, we are going to have a univariate poly that is not that doesn't have the multilinear representation, because the power of the variables will be greater than than 1, right?
Yeah.
And once that is the case, if you want to, when we're doing univariate, they say you can only represent a polynomial in d plus 1 points. You understand? Which is any random
Yeah.
point. But for the sake of simplicity, so that you don't need to start adding a lot of things in your proof, because if you don't go from 0 upwards, you need to now send the points where you use in doing your evaluation to the verifier, and you don't need that. So it's better you just start from 0, so that the verifier too will start from 0. Does that make sense? All right. So now you do your degree, and you now say number of evaluations will be d plus 1 point, which is degree plus 1 point, right? All right. Now you now say for I in number of evaluations, you're getting value from I, like for instance, value from I, which is 0, because you are starting from 0. And you now do partial evaluate. Okay, partial is supposed to be partial evaluated, or partial eval sample is equal to the current polynomial dot partial evaluate, and you're partial evaluating at the first index at this value. So when you come again, it's going to be value 1. The next time will be value will be the first time value will be 0. The next time value will be 1. The third time value will be 2, which means we have evaluated at d plus 1 point so that we can represent our polynomial. So, and what is happening here, what you need to know is that there's a chain of partial evaluation that is happening here. Because as you're partial evaluating this polynomial, which is your sum poly is partial evaluating your product poly. Product poly is partial evaluating your multilinear polynomial. That's why I say this is where the heavy lifting is happening. But you see the code is small because we have already created the chains already downwards. Now, so once you do that, we now say let evaluation be equals to partial eval, this guy, dot add polynomials element wise. I'm thinking of a best way to explain this stuff. I need to open something. So, our sum polynomial, right? Eh? No, don't worry. Our sum polynomial is holding two product polynomials, right? Are you following? Our sum polynomial is holding two product polynomials, and the two product polynomials are holding two multilinear polynomials. So the moment you do sum poly dot add polynomials element wise, it's going to go to the product poly, right? It will add, so it's going to go to the product poly. Inside the product poly, to get the multilinear, it will first add those multilinear that makes up the product poly together, then add the two product poly together to get one one polynomial. Then now it's going to perform a sum on them to have just one value. I don't know if this thing I said is not confusing. Does it make sense?
No.
Eh?
No.
Who say no?
Can you imagine?
Okay. How do I explain this thing? Okay, let me write. Okay, I think we can just use the test.
Okay.
Yeah, we can just look at the test. Well, this test is even more confusing. Okay, test generates. Okay. Well, this test is even more confusing. Okay, yeah. I explained this thing. Okay, let me write. Okay. Yeah.
This is
Actually, look. Okay.
So that's question.
Yeah, can you see my screen? Alright, so I'm going to use the same polynomial I have here. So let's say we have 2a, right? We have 2a and we have 3a, right? We also have 2a times 3a. So this is multiplication. Yeah? Okay, let's go down. All right. So if we evaluate this 2a over the Boolean hypercube, sorry, let's say okay. So we are partial evaluating this guy at 0, 1, and 2. So let's say we partial evaluate 2a at 0, 1, and 2. I'm thinking of how to arrange this guy. So, okay, let's see. Okay, let's evaluate this over the Boolean hypercube first to get the evaluated representation. So this is going to be 0. This is going to be 0, 1. This one variable now is going to be 0, 1.
Yeah.
Okay. So this is going to be this 0, 2, and this will be 0, 3. Wait, I'm trying to get why I've forgotten what we did that we got 0, 0, 0, 2 and 0, 0, 0, 3.
That's, I think, 2a plus 3b.
Hmm?
I think 2a plus. I think 2a plus 3b.
I'm coming. Let me see.
Wait, 0, 0, 0, 0,
2,
2.
0, 0, 0, 3.
Okay, that's 2a, 2ab and 3ab.
Okay. Yeah, that works. Yeah. Is it 2ab plus 3ab?
No, like they are different, but
Yeah, okay. 2ab plus 3ab.
3ab.
2ab, 3ab. Okay, yeah, I think this works. Yeah. Okay. So if we want to get our invariant polynomial, so if we do, I've done this thing before. The thing is catching my head. I can't remember again.
What is that?
Like
that reduce, right?
Yeah.
If you reduce, you want to reduce.
Yeah, it's a reduction. So there's a plus, right, in between the.
Yeah, there's a plus in between them.
Then let's just outline their evaluation forms.
Okay, this will be 0, 0, 0, 1, 1, 0, 1, 1. So this will give us 0 here. This will give us 0 here. This will give us 0. This will give us 2. This will give us 0, 0, 0, 3. Here to give us 0, 0, 0, 2, and 0, 0, 0, 3. Yeah.
So we now do element-wise
So the reduce
multiplication.
So
For the one on the left, like that 2ab times 3ab. So under it, we're
So-
just going to.
so we have 0, 0, 0, 6, and these two. Let's just say it's coming this way. So we have 0, 0, 0, 6 as well here.
Then now we can now add them element-wise.
Add them element twice.
Yeah.
Okay, so if you add them element wise, we are going to have 0, 0, 0, 12. But no, this is not what I'm looking at. Okay, so if we now partial evaluate, okay.
I know how to partially evaluate.
No,
We'll partially evaluate each of them.
before we do this.
Yes, before we do this.
Okay, so
This is reduced.
then when we okay. No, what we are trying to do is basically like getting the univariate polynomial, like how we got the univariate polynomial. That's this thing that is partial evaluating from the sum poly down to the individual
So the
multilinear, then summing everything together. You know, normally if we do this thing, we are supposed to get 0.
1, 2.
We are supposed to get 0, 24, 48.
When you do it.
Okay. You know, like, okay, yeah. So when you partially evaluate each of them, so let's just copy this out and go down so that we like do the partial evaluation.
What are we copying, sir?
Let's just copy everything.
Okay. Everything.
Yeah, but we'll clean some things and we paste it down.
Okay. Alright, in copy, so you copy.
Yeah. Just
How am I going
press
to?
and hold. Just use your hand.
Okay. Okay. Alright.
Let's off this back.
So what are we cleaning?
Let's clean this evaluation. Yeah.
So this is what we are expected to
Yeah,
get.
this is what I expected.
Um,
Let's just put it by the side.
0, 24, 48. Yeah.
Okay. So when we want to evaluate at, like when we want to get, can you index the 0, 24, 48?
This is 0, 1, and 2.
And 2.
Yeah.
So we need a polynomial such that when we evaluate it at 0, that is our univariate polynomial, right? When we evaluate it at 0, we want to get 0. When we evaluate it at 1, we want to get 24. And when we evaluate it at 2, we want to get 48.
Invariant polynomial.
Yeah,
That is
univariate.
a quadratic. You
Yeah.
get a quadratic.
Yeah, it's a quadratic.
Why do we need that?
Yeah, because if we do this multiplication outright,
Yeah.
like if we are just dealing with these coefficients,
Yeah.
when we do this multiplication, we are going to get like
2a
a
squared,
square,
b squared.
a square, b square, right? And in order to represent that polynomial, since the degree is 2,
Yeah.
since the degree is 2, we need 3 points.
Yeah.
So that is the essence of us getting these 3 points.
But I get your point too, but what we are doing here, we are dealing with multilinear. Why do we need to do it?
Because for every round in sum check,
Yes.
the prover generates a univariate polynomial, right?
Some check.
Yes.
Yes, that is true.
Yes. So now we want to do some check over this big,
Over multilinear.
over a sum of products of
Of multilinear.
multilinear polynomial.
Okay.
So one thing we would have done was to multiply it
And
Right.
sum it up.
and then do the sum check protocol,
Yeah.
right? But if we multiply it and do the sum check protocol over the answer we get, if we do this multiplication, we're just going to get an array of 4 elements, right?
Okay, I still don't. So this one now, this univariate you get, is it in terms of A or in terms of B?
Okay, this one
Yeah.
is in terms of A.
How about B? Where did we go to? So if you now want to
No, it's step
go
by
back.
You know it's a loop. If you
Yeah.
do that place where
Okay, you
it's
get
a loop.
A first. This
You
is just
get-
for A, then
yes.
you would still get for B
You
separate.
get another one for B.
How do you now bring them together?
You don't need to bring them together, right?
Since you are, for example, now this one I'm having 6A squared B squared, right?
Sorry. Let me. You understand the flow of sum check, right?
Yeah.
Now, what in sum check, what you do basically is for every round you generate one univariate polynomial,
Yes.
and for that round you're dealing with one variable. In the next round, as you're coming again,
Yeah.
you're now working with the next
Yes.
variable, and by then the first variable is no longer there. It is
I
that.
get it.
That's what we are trying to do
I
here.
get it.
You understand now?
Yeah.
So what this place we were that we're explaining is the sum check for the that will handle GKR protocol.
I get them. I get it.
Okay.
I think join this one. Come
Which meeting did they use for the end?
Okay. Wait now.
Okay. This thing, PW,
PWEC. Like,
CVB,
yeah.
Yeah, this link, man, the same link.
Yeah, we don't use the link anymore. But that was the previous one before this one. So we'll just be switching.
Alright. When he says he understands now, sure.
Okay. Sorry, let me just verify the recording again. Okay, Gabriel, are you good now?
Yeah, I'm good.
You're good,
I'm
right?
good. I think I get what is happening now.
Yes.
Because basically that was where I was stuck. And I don't know how to continue. So I'm wondering, like, I have two variables, and when I take that, how come it's just one? So what it now says now, just like I understand that when we are doing something, when the verifier send a random challenge to the prover, that is where it will, the prover will partially evaluate. So we don't necessarily need
to think about that one again.
variable again. So it will just go to the next one. So here, since we have just A, so we need to get A separately for the first round. Then after that, we now get B.
for B.
But it's quadratic. That is why we are having 3 points.
Makes
Like
sense.
that.
Okay.
So not to switch off.
Yeah, let me. If I just share it. All right. Back to business. Samuel, we are back. All right. So, so you understand, Israel?
Yeah.
Are you good with what's happening here now?
Partially. I have to too much information. I don't learn that. I have to check it on my phone.
All right. So now, so when we, okay, sorry, I'm in the test. No wonder they think they confuse me. All right. So this generates round pollings, like I said. it gets the degree of the polynomial and do d plus 1. So our number of evaluations, which is like an array that will hold the evaluations now, will now be this vector, and it's going to be with capacity of number of evaluations. So we are going to loop from 0 to number of evaluations, and we are going to say at 0, because we are starting from 0, which is I. So, and since we are working with field elements, we are doing f from I at U64. So this is what we are doing. So this will be 0. So we are now going to do partial evaluated sum poly. Now it's going to be current polynomial dot partial evaluate at the first. So this 0 here means the first variable. For instance, we have a, b, c. 0 here will represent a. If we had used 1, it's going to be b, that we want to partial evaluate at b. But why we put 0 here, it means we want to partial evaluate at the first variable, which is a. Now, and we are partial evaluating at this value, and this value here is 0 at the first iteration, which means it's going to go d plus 1 time, right? That d plus 1 time that is going to go. Now, as it's doing that stuff, since you remember we are looping through some polynomial, and some polynomial is holding product polynomial, and product polynomial is holding two multilinear polynomial. So once you do partial evaluate, what exactly are we partial evaluating?
Anywhere we see.
Yeah? Like once you call partial evaluate, what exactly are we partial evaluating?
The first
Which polynomial are we partial evaluating?
the sum.
No. What we are partial evaluating is the multilinear. This sum poly and product poly, they are not actually polynomials. They are just structs that are holding polynomials. So what we are actually evaluating is the multilinear inside the product poly. Does it make sense?
Yes.
So this is a chain of partial evaluate functions. So as you call this partial evaluate, where is it? As you call this partial evaluate is calling the partial evaluate inside the product polynomial. And the partial evaluate inside the product polynomial is calling the partial evaluate on the individual multilinear polynomials. So it is that multilinear that we are actually partial evaluating. Does it make sense?
Yeah.
Now when we partial evaluate that multilinear, remember now we have 4 multilinears, right? When we partial evaluate them, now in the first product poly, it has 2 multilinear. In the second product poly, it has 2 multilinear. So once we partial evaluate them, we multiply. We have 1, 1, which will now be in the sum poly. Now in that sum poly, we sum, right? So that is what we are doing basically to now get one value. That one value now is what we are going to push inside this evaluation. So by the time it finish this
What do you mean by one value? One field element.
One field element. So by the time we finish this thing, we are going to have 3 values inside this evaluation array. Are you following? When you start doing this thing, it will be making sense, don't worry. So that is how we are getting our univariate poem. So this loop you're seeing here is just looping through d plus 1 point to do the partial evaluation, which is how we represent our univariate poly, because it's going to be a quadratic this thing. All right. Now back to this guy. All right. So now, once we get our univariate poly, right? Are you following somewhere? So once we get our univariate poly, we are going to append it into our transcript, right? Now once we append it to the transcript, we now push the univariate poly to our round polynomials. Then once we do that, we generate a random challenge. Then this random challenge, we are now going to push it into the random challenges array. Then here we are going to partial evaluate the current polynomial to remove the first variable, and we are basically setting current polynomial to current polynomial dot partial evaluate the first variable at the random challenge. So this loop will come again, and that is how it will continue until it has gone through these rounds based on the number of variables that the polynomial has, and it will finish up there. And by so doing, it's going to be pushing all those round poly to the round polynomial variable, and the random challenges is generated to the random challenges this thing. So this is what makes up our proof, which is what the verifier is going to use. Does that make sense? Now, if we look at the verifier is basically taking in the proof and the transcript. So what it's doing basically is it will append the proof, which is the claim sum. Remember that the step the prover takes is the same step the verifier will take. If not, they will have different random challenge. So since, if you look here, you see that the prover is first, where is it? If you look here, see that the first thing the prover appends is the claim sum. Similarly, the first thing the verifier will append is the claim sum he got from the prover, right? Then the verifier will now set the current claim sum to that claim sum, and will now create his own random challenges, which is going to be based on the number of round polynomials you received. Because remember, the round polynomials was generated based on the number of variables the polynomial have. So if that is correct, the round polynomial is going to be equal to the number of variables. And that is why it's using its own random challenges to be the length of the round polynomials. Now, the reason why the prover is getting this is because the prover needs to for the prover to evaluate the round polynomials, right? For the prover to evaluate the round polynomials, the prover needs to interpolate so that he can evaluate it. There are some persons that didn't do the evaluation, they just added the first index and the zero index, right, to do their own. Well, me, I'm interpolating because I'll interpolate at, you know.
I think that one is.
Which one?
Instead of
I don't know why it's better, sir. Okay, my internet is shut. Oh, my phone has gone off. I think my phone has gone off. Where is it? That's my phone. My phone is there. I think it has gone off.
Maybe your charger.
Yeah, it's gone off. I'm not with my charger.
Type-C.
Yes, no, not Type-C.
What do you mean?
I don't get money. iPhone charger.
Where our charger?
They what? What is it? Biggie. What is this? Baby. Wow.
Give me buy me
white t-shirt. As in, that's true.
Who be baby? I'm not. Okay, it's coming on, yes.
It's something I'm born with.
That's it, they go by fast.
I'm waiting to soft now. Let me use this. Okay, I'm not connected to some. I'm connected to a pretty good
Is it going?
Where they go?
Which one?
Alright, somebody else.
Web 3 group.
Okay, 2G5.
So I should do 2G, 5G. That's standard.
No, use Web 3 group.
Yeah?
It's not good.
Not going. Not going.
Where's my own?
Alright.
It is sound.
Alright. Thank you. All right. Can we continue? All right. So Dean was saying something. So I noticed that in some person's code, the instead of interpolating, they were just adding the index 0 and index 1. Yeah? I don't know. I don't understand why that works.
That's for the previous, that's when it's multilinear.
No, even in the univariate, that univariate, they don't interpolate.
No, to get a univariate, interpolate your multilinear in evaluation form.
To get your
To get your univariate polynomial, you interpolate your evaluation point of multilinear to get that univariate.
Yes.
But once you've gotten the univariate, to now get the 0 and 1, you can now add like to evaluate 0 plus evaluate 1.
what they are doing, they are not evaluating that univariate poly, they just get it index 1, index 0, index 1.
You can't use a univariate poly. It has to be multilinear. For you to do that 0 and 1, it has to be a multilinear in evaluation form. You can't do univariate coefficients. Because if you are doing 0 and 1, you are basically saying the coefficient of constants plus coefficient of the x, which is not correct.
Okay. Let's fire that. So, are we good? So, can we continue? Alright, so for you to interpolate, like the way I did my own interpolation, I take my x and y points, my x and y values, right? And remember, your x values are the points where you use in the 0, 1, 2, where you use in like getting your univariate polynomial, like the values. Let me show you what I'm talking about. When you did this guy, you're returning just these evaluations, which is an array of values. It's not actually a polynomial per se. It is just y values. Are you getting it? Yeah, for you to now interpolate it to make it a polynomial, you need the x values. And the x values we use in getting these y values was 0, 1, 2, right? So yeah?
That with evaluation. And equating it to like vector of zeros. What is the difference? Or is there a difference?
Which this thing?
Like when you're initiating a vector, then you use with capacity. And then you use just equal to vector 0, then specify like length. What is the difference?
So that one so in that I don't know I don't know the when it comes to memory usage and all of that. I can't say, but I think the way you use it will be different, because for this other one you just be pushing,
This one is push, but that way
but that one you have to use the index to set the value. But I don't know the both of them, the one that is more efficient, so I can't say. All right. I don't even know. Eh? Eh? Okay.
Let me
Okay.
just say something about
Alright.
it. It's kind of like about like memory allocation, right? So when you say vector capacity, you're basically telling the computer create a vector, yes, and keep this amount of space for me.
Yeah.
So it may get up to that, or it may not, right? But I'm telling you, just keep this amount of space.
Mhm.
So when you just do like a normal vector, you can push, right? Because the values are basically stored. That's what I know, like that's what we call the stack and the heap, right? So the stack has a fixed size, but the heap can grow, right? So when you create a vector, you're basically telling the computer allocate space for me on the heap. So the vector is growable. So that's why you can push to it. Because it doesn't matter how many times you want to push to it, you just keep growing. Right? And that is also the issue like with the slides. The slide is not growable. So you cannot push to the slide. If you want to let's say modify the slide, you need to at a particular index. Like that is the particular index you want to modify. I don't know if that's answers.
Okay, I think from this thing you explained now,
Vector.
It's using heap.
Vector is this.
So that it keeps it.
so
You can keep adding value.
but what he's saying is, you know, what's the difference between doing vec with capacity 3 and doing vec and you set 0 that capacity, so it will do 0 to like it will create 3 zeros, right?
Okay.
So it's the same vec which is going to the heap, and the other one too is the same vec with the capacity, right? But now for the second one, if you want to update, you just do that vector at this index equal to this, but the other one you're just pushing. So, and both of them are not slices, they are still vec. So what is the difference between the two?
One you are setting value.
Can you push to a
value
vector capacity?
Yes.
When you create a vector capacity, can you push?
Yes, you can push.
And you can
There's
change that.
there's nothing.
But you cannot go beyond that capacity.
No, you can. It is just you can go beyond that capacity. It is just saying that when you start it with capacity, you are just preparing that vector that this is like basically the amount I'm expecting to receive. But you can go beyond. It means that that vector will have to like extend itself again. You know, on a normal day, if you just specify a vec, it doesn't really know how many is going. So based on your memory, like based on your system memory, your system can decide, oh, in batches, what I can take is maybe 1,000. So when it extends that 1,000, it's like extends itself like another 1,000 capacity. Like it basically depends on your system's capacity. But the thing is that when you initiate your vector with capacity, it means that you're just like preparing that, oh, this is maybe the amount I'm expecting this vector to have. So when you're pushing, like it doesn't need to extend itself again because it knows that, oh,
This is
I was already exactly.
So basically no difference then.
With initializing this, there is basically no difference. It's just that one is pushing, one is appending, and one is
No, I think the first one is only initializing, not instantiating. That one that has 0 and
What do you
function,
mean instantiate?
you can just initialize and say I want to have this and you don't have value in it. What you are doing, you're already giving it value for all of them.
But we are the difference. We are not looking at implementation difference. We are looking at we are looking at cost difference.
Yes, nothing is inside.
Actually, there is no null.
There is no null.
So instead of doing that thing with vec, right? you can do it with slice. Can you do that with slice?
Like with the size, yes,
You can do that with slice,
Like the
but you
initializer
cannot
with
push to
zero.
slice.
No, you
You
cannot
can't
push.
push.
So that would have been better with slice because if you do it with vec, it's like it's still the same thing. So, but if you do it with slice, you can now use the slice to update the particular index.
So you
But can you update slice?
You can update.
so you can't. So slice it at that time.
Okay.
Yes, slice.
Eh?
Slice is
Slice
the
is like
window
a
into.
window of
Into an
deck
array.
or an array.
I dey hear you.
So can you
Like the slice happens.
Eh?
can you put
Nah, no be.
Sorry, I want to quickly say something you mentioned before. Say you have a univariate 246. If you evaluate it as 0, what will it be? Univariate 246.
That is
If
about
you do it now.
If you evaluate it at 0,
You
if
get
you evaluate it at 1, what
Do
will it
it
be?
now.
It will give you 4. So like because
I
I'm
don't
going back, no.
Okay, yes, that thing
So,
we're talking
yes.
about, yes.
So like
There's no need
so
to
what's the
interpolate
issue
again.
with what's the issue with adding 0 and 1?
No, he was saying when you have calm down. This was what he said. He said that some people are doing univariate 0. That's the element at 0 plus
Yes.
univariate 1.
Yes,
and I'm saying
and
that is wrong because the univariate we are using coefficient form, so you cannot say it's constant plus x.
It's not like
You have to
multiplication.
evaluate first.
Now here is question. That's why I say when you evaluate at
When you
0,
evaluate
what,
at 0, what do you get? You get that first
You cannot
value.
say the same
When
thing.
you
and that's the same. That thing you now say that is wrong. It's not wrong.
No,
you're not
you said see. There are
Yeah,
two things we are
evaluate
saying
at
now.
0, 1, 2.
What you
I've
mentioned
Is
was
that
you took element 0. Let's say I have 2, 4, 6. You are doing 2 plus 4.
If you evaluate at 1, you get
Now
that
it is
value.
necessarily not like wait oh
That's the same thing he's saying
you
now.
evaluate 2, 4, 6 at 1. You are not getting 4.
You are getting
You're getting 4.
It depends.
You will
You're
get
getting I checked
Jesus
it.
Christ.
I checked it.
Wait. Please. Let me say something.
I saw the code. But if that thing
Wait,
works,
wait.
if that thing but if that thing they did work, there's no need to evaluate because evaluate is even expensive.
People should hear me now. You have a quadratic univariate 2, 4, 6. That is 2 plus 4x plus 6x squared. Evaluate that at 0. What do you have?
No, wait.
La lulele.
What do you say your univariate? Please, who started univariate in evaluation form? Raise up your
Everybody is correct. Everybody is correct.
Yes.
So that means there's no need to
But we can't
evaluate.
No. Everybody is correct. Because it depends on your approach.
Exactly.
It depends on your approach.
And I'm saying, I know almost everybody here, 99% of us, did not initialize our univariate in evaluation form. It is that simple.
Yes.
But some persons did.
That's what I'm saying now. Is implementation details? Yes, that is true. Implementation details. But is that not what we are doing
But
here?
Uche, you first said it is wrong. That it's not.
I said it was wrong because I know that. Calm down.
In coefficient form, it is wrong. Yes.
Yes.
When evaluation form, it is correct.
But who did the evaluation
My
for
God.
you?
This guy dey talk.
That's not Uche is saying that if you interpolated, if after getting those three values,
Exactly.
you interpolated to get a univariate polynomial,
And then you're not trying to.
and then you're trying to take index
element
0
as 0 and index 1.
That's
It's
wrong.
wrong. Simple.
Yes.
That's all I'm saying.
Yes.
Did you hear what he
If you
said?
don't
That means you
interpolate,
interpolate.
if you pass it
First.
into like a
What?
multilinear,
That's if you don't
do not
interpolate it.
interpolate.
I give my
and it's
credit.
in evaluation
If you
form.
don't understand it, I
Evaluation
don't.
form.
May you rest.
You can just pick
I
the
don't-
values at index 0
Zero
and
and
index
index
1,
one.
but you don't need to evaluate.
Yeah.
If you call evaluate on that multilinear, it will panic.
That's why I said
Yeah.
in multilinear evaluation form, it is correct. But we are talking about
We're
univariate
talking
here.
Univariate evaluation
In
form.
coefficient. Don't say. Leave am. Don't say. Bring out your laptop.
I said one day you rate evaluation form.
Yes,
But everybody get the point, right?
Yeah.
Yeah, I don't tire.
Let's make us
So
Okay.
I noticed something. That univariate polynomial does not accurately represent the full FABC.
Is it the FABC
Eh,
or
let's say-
the univariate polynomial for particular?
Yeah, it doesn't represent
It does.
that univariate polynomial itself does not accurately represent no, you have already summed over 0 and 1, right? Then you're supposed to have it only on let's say on A
Or A or
or B. Like it doesn't actually represent the actual real quadratic equation
for that variable.
for that variable.
It does.
Like I noticed that it represents it works for some check. But when you want to do real evaluation on that part using those values to give it a wrong answer. Because what you're supposed to do is that you're supposed to do it if you are doing it, you're supposed to do what we're doing is we'll leave A at 2 and the rest will be 0, 1 and we'll leave A at 2. The other one will be 0 and the other one will be 2, 1. But what we're supposed to do is we're also supposed to say 2, 2 at the ending.
That is 2 0
2, 0, 2, 1, 2, 2.
2.
So as to give us the accurate full representation.
But the way we went about it, there's no need to do that.
Yeah, that's what I'm saying. I'm
Yes,
saying it
that.
works for some check. But when you want to like actually evaluate that, let's say you want to use, you can't use that to represent the real quadratic equation for that particular
No,
You
for that
can now,
particular
that's-
variable, it will work.
for that particular variable.
It's like for the particular, like the univariate polynomial for that particular variable, those 3 points are correctly represented.
Okay.
But wait, I'm coming. But if you reduce, right, the final polynomial you get, if you reduce first
Yes.
before doing the partial evaluation, then it's going to be wrong.
Wrong. Yeah.
Right,
true.
because that reduced form, you need to factor in that 2 0,
Quadratic.
2 1, 2 2, even 1 2, and 0 2.
Okay, that makes sense. So that means that if I have a simple quadratic equation now, right, and I'm going to do 0 0. Okay, I do 0 0 0 1, 1 0 1 1, 2 0 2 1. That is what we currently have. We have only 2 0 and 2 1. So if I want to actually represent it, I'm not supposed to have 0 2.
No, you're
1
supposed to have 0 2 1 2
1 2 and
Yes.
2 2.
and 2 2. Yes.
That is what accurately represents
That's
that
what-
quadratic. But for some check, we only do on the Boolean hypercube, so we only do zeros and ones. So that's the point I'm trying to. I noticed.
Wait, are you talking about representing the
Yeah,
full,
we don't talk
the
about
full
it
this
now.
thing, or
Yeah, for 2D.
Please don't scatter what
We
we
don't talk
what
about
we
it.
have already.
Even for us to
I
talk
don't know
about
it.
it.
Yeah, animation is
It's not
sufficient.
Huh?
Like, you dey talk.
Now we dey do.
But But we're together, right?
You guys are.
And we are not together. I don't know where it's getting to 240.
No, like
We know that
Eh?
one already.
the product poly.
Yes.
If you want to actually represent it in the correct form, you need to use the 3H, which is the 0, 1, 2.
Uh-huh.
So, but then for some check, we are not really interested in the full representation.
Yes.
All we want to just prove is that the sum over the Boolean hypercube
Yeah.
is the sum, and I think the Boolean hypercube is sufficient enough to represent it.
But the thing is, the reason we are not representing it now because we know that the moment we multiply that thing, it gives us this thing, which for us to actually work with it, we start looking at 3AC and all of which was why he said for those that are ambitious enough, they can find out how to do that with 3AC. They carry us go back.
He was just stressing it.
Okay.
He's an observer.
I worked at the Observer.
So everybody's together now, right?
We're not together, I don't know him.
I don't even confuse with you.
Okay, sorry.
Please, what was I doing? Now from GKR we come something.
Nah, I can't bring us back.
Sorry, just.
It's two observers.
Yes, now.
The best way they report to not finish.
You don't finish this.
I never finish.
I see when they do cases. Sorry, please. Where did I stop? I beg. I don't know what.
You stopped at the.
We have talked about proof now. We're talking about verify.
Yes.
So we're talking about how.
Samuel, you're the one that brought us here.
You don't know before.
Yes, should I go back to GKR?
What you were saying was you're trying to show
No, I
us
don't
how
know.
Yeah,
that is
I'm good.
Okay. Oh, let's go back to GKR. I beg. All right. Mm-hmm.
Can I see that your round code is just one?
Which one?
There was a function that I saw round code.
This one.
No, like there was a function you declared round code.
Function that I declare round poly.
Yes.
There's no function like that here.
Was it a function that I said? I don't know what I said, but I said something like
This
round
one.
code.
Field of one of your structs for the
Oh, okay.
GKR.
Was it struct? Okay. Okay, for round code.
Where? Okay. Where?
You passed it, I think it's down.
Line 59.
I think it was a for loop just now. I saw for round code.
For round poly.
Yes.
I was there now.
For round polynomial, sorry.
Yeah, Abi.
Go back. See, go back.
59, 59.
For round polynomial. Round the root. Okay. So that round polynomial stuff, that reference that you did, there's a struct of Abi that is called round polynomial.
Which one? This one.
Yes, round it.
So this round, when you're making use of for loop, you can either do for I.
Or you do for.
Yeah. So instead of me calling I like naming it something that I want to know what it's looping through, so I know how to use it. Because I is just index. You understand? But this place now we are not using index. If I was doing for I in 0 ... something, that's why I'm working with index. But here I'm not working with index. Here I'm working with the actual stuff I'm looping through. That's why I say for that thing I'm looping through. I'm looping through the round univariate polynomials that is in the proof.
Okay,
that
I want to see that one.
Eh?
I want to see the code for that one. That was what I was looking for.
Okay. Alright, so this is a prover. As the prover is doing his proof, is generating univariate polynomials here. And for the univariate polynomial is generating, is pushing it into this round univariate polynomial. So, and now in the proof, we are setting this round univariate polynomial to anything that has been pushed into this round univariate polynomial array. which means if this guy went 3 times, there will be 3 round univariate poly inside this array. That is what is sending now to the verifier. When the verifier takes this proof, the verifier is also looping through the number of round univariate polys that the prover sent. Does that make sense? So, and it's getting the actual round polynomial that is looping through. So if you're looping through something, you're getting, so for every instance of that loop, you're getting the actual thing you're looping through. Does it make sense? So normally, if we want to rewrite this thing, we would have just done for I in 0 ... this guy dot len. So now when we want to use the univariate poly, we are going to do something like let's round polynomial be equal to this round univariate poly now at I. So this is what we would have done, right? But you see, as I did this is what we would have done normally, but there's no point doing that anymore. So we can just get it directly as we are looping without going to see. We have done added extra line and this thing, not necessary. So we can just get this stuff directly from here and we are good. Should we now go back to GKR? Are there people still following this GKR representation we are doing? Yeah? Okay. Alright, so let's go back to the verify. Like I said, what the verifier is basically doing is, the verifier is most likely going through the steps that the prover did, but the verifier is not performing any computation. The only thing the verifier is doing is getting the things that the prover gave to him and is using it to compute, like just compute something without actually like performing the actual evaluation and all of that, because you know it is in that evaluation that the heavy lifting is. So the verifier is not performing those evaluations. It's just getting the things the prover is sending to it and computing its own claim, its own expected claim, right? And he will not trust everything that the prover gave to him until he has gotten to that input level, because at that input he knows this is what I gave to this guy, right? So it's going to use the input to compute its own WB and WC, and once he uses that and compute his own expected claim, he now checks it with the expected claim that the prover sent for that particular input layer. Does that make sense? And if it matches, then the verifier accepts. So the way the verifier computes its own expected claim, it doesn't need to do any evaluation, all those plenty things that the prover is doing, like evaluating the FDC polynomial. But it's basically going to go through the same step that the prover went through. Because if it doesn't go through that step, the sum is going to generate, the random challenges will be different. Does that make sense? Alright, let's fire down. Alright. So the verifier is basically like setting up what the prover is also setting up. So we have our transcript, we have our alpha and our beta initialized to be 0, and we have our previous sum check challenges. So we are going to be using this to do our computation. We'll see where we'll be using it. Now, the verifier gets the W polynomial, because this is also what I think I just need to say. The verifier gets the W polynomial, right? And he checks if the length is equal to 1. If it's equal to 1, he appends and, append 0 to it, add it to the transcript after converting to bytes, then generate a random challenge, use the random challenge to evaluate that W polynomial to get the first claim sum. Now with that first claim sum, once the verifier enters this loop, where it's looping based on the number of layers in the circuit, right? Because the verifier knows the circuit. So the first thing is going to check if the claim sum he computed is equal to the claim sum that the prover sent at that particular layer, right? So if what he computed and what the prover sent doesn't match, he returns false. Are we good?
Yeah.
All right. Now the verifier moves to the next guy. This is where he now wants to start his verification. Now, you know we went to the sum check, the GKR sum check, where the verifier accepts the proof, right? And this proof, it accepts the proof and transcript. So now we are passing the proof of the particular layer that the verifier wants to verify, because every layer has their own proof. Does that make sense? So we are passing the proof of the particular layer the verifier wants to verify. Once we pass that proof, so we are storing whatever the sum check verifier is returning as verified result. Now we check without do if verified result is proof valid is not true, is going to return false. Are we good? Are we good? All right, it's going to return false here. Now once it passes this line, it gets the challenge, the sum check challenges, which is the random challenges from the verifier that the verifier will bring. Once it gets that, now this is where we want to do some little this thing, and this part too is kind of important. So watch what is happening here. We want to get our WB evaluation, and our WB evaluation is coming from the prover, except the input, the evaluation of the input, because the verifier also has the input. The verifier is not supposed to get the input evaluation from the prover. So we are now checking if layer index is less than circuit.layers dot length minus 1. Get the the WB evaluation from the proof, which is what the prover sent. But else, use the input to evaluate the WB and the WC. Is it making sense? Yeah. Are you following? All right. So now, and I have this, I've already shown us this function before, this evaluate WB, WC. So it takes in these challenges, yes?
I'm trying to calculate when it's not going, when you're going to calculate. So that's for the first.
That's for the last
layer.
The last layer, which is the input layer.
Yes.
Yes. Does it make sense? You know, in GKR structure, layer 0 is output. Does it make sense? Yeah. So I had to work with that normal GKR structure instead of working with the inverse. So that's how this thing is going. So once it starts from 0 and loops, as it's getting to the last one, it's not going to compute, like it's not going to get this guy from the last one, the Chineke.
Yeah, press the switch off, so that you know.
Before the ending.
15 minutes. Take yourself. For 15 minutes, please. Let's just continue.
Yeah,
when it
finish, we'll do this thing. So, I don't know. Do you understand what's happening here? You get right? So now, this is where.
Sorry, can we? If there are 3 layers now.
This is going to stop at layer 2.
Which is the output layer?
If there are 3 layers.
Okay, the way you arrange it on. So
mine is the output is layer 0. Okay. You understand? So if the length of that array now is 3, right? It's going to stop at index 1, because index 2 is the output now. Does it make sense? Okay, so now we have gotten our WB evaluation and our WC evaluation. You see that the only part where the verifier is actually performing an actual evaluation is where it's evaluating the inputs, right? So, but every other thing the verifier is using is not doing any work, it's just getting it from the prover. Now, this is where we are computing our expected claim. So this place that we are computing our expected claim is just basically doing what the FVC polynomial does, but now we are not evaluating FVC again. We are just using that linear combination, all those things to compute this stuff, that adimolite stuff to compute everything. So, are we following?
Yeah.
Should we go to that function? Eh? Should we? It's the same thing that Oba did though. So let's just go there though. Let's go there. So the thing is, you see that we are doing expected claim. If layer index is equal to 0, is calling a different function. This one now is trying to compute verifier initial claim, which is claim for the output layer with the layer 1. You understand? Now, but for other layers from layer 1 downwards is using the folding. That is why we are passing in alpha beta here. Are you following? All right. So let's hit this guy. Okay, I'll show you something when we get there. So when I was working on this function, I had a problem. So I now figured out that for you, the way this function works, right? You're going to follow the same pattern with which the prover used in generating their RIBC. For instance, let me show you something. So at first, what I was doing, I was combining this, where is it? Yeah. Okay. So I was getting this initial challenge. I was combining it with the sum check challenges to evaluate everything at once. But it was failing. It wasn't working. So I now went back to my prover. So if you go to my prover, you see that the way my prover is computing the ADI BC is it partial evaluates with the first random challenge. So I followed that same pattern in computing my claim. That was when it worked. So where is that guy? So what I did first was I get my ADI ABC, which I have access to, which is the verifier have access to the ADI ABC and also to the circuit, but it doesn't have access to the WB polynomials, right? So I get my ADI ABC and using the circuit, so I'm passing in the circuit and I'm passing in the layer index. So I get it from that guy. Now for me to remove the A from that ADI ABC, I'm going to partial evaluate A at arrow A. Are you following? You remember arrow A, Abi? Alright, so I'm going to partial evaluate ADI ABC at arrow A. And once I do that, I'll get my ADI ABC. So you see this thing is repeating in like 3 or 4 places. I need to look for helper function that will just be doing this split and divide for me. So what I'm going to do here, so I'm basically getting the midpoint of my sum check challenges for that particular layer. Then I split into mid to get the arrow B and the arrow C. Then I now combine, so combined challenges will now be, so this is basically, what I'm doing here basically is like creating a vector that will combine the arrow B and the arrow C together so that I can use it to evaluate at once. So what I'm doing here now is the arrow B length and the arrow C length is going to make up the length of these combined challenges. Okay. But wait too. Well, if I just say something, why don't I just, if I just evaluate at sum check challenges, it's supposed to work now. Abi?
What is it?
So look at what I did here. I splitted sum check challenges into 2.
Yeah.
Arrow B and arrow C. But I now combined it here again.
Yeah.
Maybe you might have
Maybe did you need like to find the
I now combine it here again. So I could just use some check challenges and run my
check for
guy
any,
here.
check for any place you use RB and RC like aside that place.
That's the only place I use it. But wait, just shoot. Let me do that real quick. If I pass this guy here and I pass this guy here, it should work now.
No, he was saying that he kind of splits RB and RC.
Yeah, it should work. Yes, it's not showing an error. Let's see. Let's quickly check this guy. So I just want to run the test for the GKR, so it won't run everything. Eh? Eh?
It's not,
You're not in
it's
the-
not it's
Wait, sit down. See
it's
the.
not first related, it is
Wait, chill, just chill. Where am I? I'm in research implementation now, have you?
LS to check. That's LS to check.
Yes, now, yes. Cargo. What is happening? Ah, chill.
Are you in GKR?
I'm coming. Let me open that guy again.
Again.
I know I didn't delete anything now. Wait, chill. What's it just up now? What just happened? Wait, caused by research implementation. KZ. Oh.
Maybe you have not added it or you
Oh, okay. I get. I know what's happening. I just changed that stuff today. Yeah. So it was KZG PCS before. Yeah, KZG. So it's no longer that guy. Yeah. Alright, kill. See they saw. Alright, so let's look at this guy and see what's popping here. Let's see, that guy is supposed to work actually. Cargo test. Yeah. So we don't need that actually. Thank you, you're far too kind. Alright, so I'm going to work on this later. So alright. So I don't like seeing this comment though, but alright. Are we good?
Yeah.
Alright, so what we are doing here basically, it's we just partial evaluate the ADI ABC at the ROA to get our ADI ABC, our MOLA ABC. Then we use the sum check challenges to now do a full evaluation on our ADI. So this is now going to be ADI at arrow, which is a random challenge, and MOLA at arrow, which is this guy. So now once we get that, we are now going to do add I arrow times WB plus WC evaluation. You know, this is no longer a polynomial, right? So normally if it was a polynomial, what we're going to do, we blow up and do tensor this thing. So we just do this guy times this guy plus this guy times this times this, which is the same thing. This is what makes up our guy now. You know our guy. The FBC now, the FBC polynomial is ADI ABC times WB plus WC, then plus MOLI ABC times WB times WC. This is exactly what we are doing here. This is ADI arrow evaluated WB plus WC. This is MOLI evaluated WB times WC. So this is what is going to give us our initial claim. Here we are not doing the folding because we are still in layer 0. Does it make sense?
Yes, sir.
Are we following?
Yeah.
All right. Let's just quickly look at this other one. So this other one now is the same thing, but with the alpha, beta, and the previous sum check challenges. Let me look whether I'm still doing the same thing here, and I'm not doing the same thing. All right. So here now we get the previous ROB and the previous ROC from the previous sum check challenges. Split it at the middle. This splitting I'm seeing everywhere is just making me feel somehow. Should have done this thing better. All right. So now we get our ADI BC and our MOLI BC from circuit ADI MOLI MLE at the index. Remember, like Wisdom and Francis said, the verifier has access to the circuit. Automatically, they have access to the ADI ABC and the MOLI ABC. So that's what we are getting here. After getting the ADI ABC and the MOLI ABC, now remember we have a function that computes ADI MOLI when it has alpha. That's when it's for other layers. So we don't need to even repeat this stuff here. We just call that function, passing our alpha, beta, our ADI ABC, our previous ROB and our previous ROC. It's going to do the computation and return ADI and MOLI, the new ADI and the new MOLI for us. We did it now. I showed you that function, what it's doing. Right? Why are you looking like you're lost? There's this function I showed you. Let me go there. Let me go to the function. You're supposed to take me there now. Is it because you're down? Let's go there. Was it up or down? Sorry. Okay, this computes new ADI and MOLI. So this is it. It takes the alpha, the beta, the ADI ABC, the MOLI ABC, the ROB values, and the ROC values. Now, remember that this ROB and ROC values is dependent on the bits of your A. Do you remember that? Are you following? It's dependent on the bits of your A. So if your A is 2 bits, these ROB values will be 2. Will have 2 elements in the array, and ROC2 will have 2 elements in the array. Are we following? And if the bit of your A is 3, it will have 3 elements, which means if you want to partial evaluate, arrow 1 will partial evaluate at A1, arrow 2 partial evaluate at A2, arrow 3 partial evaluate at A3, because all the 3 of them still makes up A. Does it make sense? Are you guys following? All right. So, do you understand this function now? You remember this function, right? All right. So that is what we are basically calling here, passing in all the necessary arguments, and it's going to give us our new ADI and our new MOLI. And once we get our new ADI, our new MOLI, we fully evaluate the new ADI and the new MOLI at the current. You remember the previous one, we used it to partial evaluate the ADI ABC and the MOLI ABC to remove A. But now that we want to fully evaluate the new ADI and the new MOLI, we use the current. We don't almost finish that. Yeah? We have to record it for that people.
Will you still be writing?
No, I won't need to write again.
No need to write again, right? So I think for this next one, I should be. Which meeting link should we use?
It's got the
which one do we finish?
Internet dependent. Your internet is not very strong. It should just be misbehaving. I think in all of them, the one that is lighter in terms of internet usage is Telegram. Sharing screen, anyone. Telegram has consumes the side internet. It's very light.
Oh, they are be kind.
Is it?
I was begging Google to be nice. That's great.
let me just let me just I O
IOQ
Q
UGMX
U
FCP.
FCP. All right, we're in the final laps.
Sorry, let me verify this guy. Can be funny sometimes.
All right, can you guys see my screen? Can we proceed? Are we together? All right. So this is just it. So now we get our add arrow. We fully evaluate at the current random sum check challenges. Our mole arrow fully evaluated at the current sum check challenges. Now we do this thing again. That same FBC polynomial, which is add evaluated at arrow times WB evaluation plus WC evaluation plus mole that is also evaluated at arrow times WB evaluation times WC evaluation. So this is the same thing we do in our FBC, but just that here now we are not actually evaluating FBC again. We are just making use of the values that the prover is sending to run this stuff. But now in the last layer, which is that's the input, we are not getting it from the prover anymore. So the verifier is evaluating that one himself and running the same check. So if the check on the input layer passes, it means everything the prover sent from time memorial was correct or was valid. Does that make sense? So that is why in our verify, I've shown you the compute initial claim and the compute verifier folded claim. So in our verify now, where is that guy? So in our verify, we are just getting the expected claim. If layer index is equal to 0, it uses this one that doesn't need the fold. If the else is going to use this one that passes in the alpha and the beta. And once we do that, all we just need to do here is if expected claim is not equal to verify result dot last claim sum, we return false. Then we set our previous sum check challenges to the current challenge, because when it comes again, this current will become the previous. And we do this guy, I just added it yesterday after our correction in class, where Francis said that anything we are getting from the prover, we also need to put it in the transcript. So that's why we are putting this WB here. We get our alpha, we put the WC, we get our beta, and we update the claim sum to whatever this guy returns and all. So this is basically everything that we have done here. Any question?
Can you come over that WB, why you are appending WB evaluation?
This one?
Yeah.
So yes, before I wasn't doing this. Before I was squeezing twice, right? But you know, yesterday Francis mentioned that for transcript to be more secure, it is always good that anything that the prover is giving to the verifier, that they are all appended to the transcript, because the prover can come out tomorrow and say he gave the verifier 2, you understand, and the verifier doesn't have any proof because he didn't append it. So it's always good to append it so that there's always a reference point to check, okay, this was what you gave to me and this is what I appended. Does that make sense? Yeah.
Okay, don't worry. I'll see.
All right. Does that make sense?
Yeah.
Any other question?
like you can as well append the both of them.
At once.
At like
Yes,
17 or
simultaneously and then
Squeeze twice.
twice.
So me, I just want it to be different.
The goal is just for
Right,
the
that was over.
Eh?
What you do now with your body? How does it make it different?
I don't understand.
They monitor their code together.
I don't understand.
don't sabi who.
He said he wants to be different.
I don't
What
understand.
do you do?
I don't understand what you're saying.
You they monitor their code.
Man, what's your body?
How you
He
know?
showed me. He showed me now. He showed me his
We are no guests now.
Are we done?
But
Sharp, sharp,
Yeah.
sharp.
okay. Thank you. So, do we have any questions? This
Yes.
is too code
So
review.
2 more days to implement. Like
You
Friday
say-
and Monday.
You say
Friday.
You say what?
okay.
Wow. We should be good now.
We should be.
Yes.
Shoot.
Yeah, we should.
Nobody use shoot.
Sorry. But like, with what we've done so far,
So like
does
this
anybody
call,
have
who get this
any
call?
question? Huh?
It's actually clear.
It's actually clear, right? Thanks. Okay, yeah. Yes. Israel.
My question is
Because
the code.
Okay. I can hear you.
Why you implement
Yes.
I'm always astonished
astonished.
seeing other people implementation because when I'm implementing mine, I don't think of what they think of. Like, I don't know, like all possible possibilities. How will I do it? All possibilities, all cases. I
Yeah.
don't think that way because sometimes I feel that these people used to cheat because I don't know how while implementing, maybe I'm thinking one way. How do I get to that? That is basically the question. How do I get to the point that when I'm implementing all those things that I don't like, I don't pay attention to, I will pay to it because I'm not seeing it when I'm implementing, and what I'm not seeing, I can't implement. So
Well, let him finish.
that makes my code always strong. Like, it's always strong because
No, don't think about it that way.
I'm not. Alright. So
I think
Sorry.
Hold on.
Everybody will talk. Everybody will talk. After him.
Okay, so I think it's a skill you have to do.
just say it.
Okay, you guys can calm down now.
Like, you can't just start thinking of all the cases. You have to have maybe seen something behave a certain way and you be like, oh, what if this case I'm working on behaves that way, right? It's not like you are not just meant to know everything. It's this polynomial input padding thing now that we're talking about. It's just the way of thinking, oh, I've seen a circuit like this. What if, okay,
Does that not mean that I have to depend on people before I always do my sentence?
So okay, let me help you with something. So once you need to understand is, you can do an implementation the way you think about it.
But there's always a software engineering statement that says you learn better, you
Sorry.
become
I can stop the recording.
yes. So you become a better programmer